Tonight, we're floating through everything. Not one galaxy, not one star, but the universe itself. We'll explore how it began, why it keeps expanding, and what holds it all together. We'll listen to the whispers of dark matter, the hum of ancient light, and the silent rhythm of time itself. If these peaceful journeys help you unwind, I'd love for you to subscribe and join us again. And tell me in the comments, where in the world are you listening from tonight? Now take a deep breath. Let your thoughts widen. Let your curiosity drift, because the universe is waiting, calm, endless, and quietly alive. Imagine a morning so early that there were no birds to sing it into being. The whole universe wrapped in a soft, featureless gray. That gray was literal, a hot, dense fog of charged particles and photons, constantly scattering off each other so light couldn't travel far without being knocked off course. For hundreds of thousands of years, the universe was effectively a fog bank, and anything that tried to see through it would simply be blinded by the glow. Then, slowly, the fog lifted. As the universe expanded, it cooled. Protons and electrons, which until then had been a busy, jostling plasma, finally found it favorable to combine and form neutral hydrogen. In technical terms, we call this recombination, but the word understates the moment. It was the first time electrons stayed put around nuclei rather than chasing photons across a roiling sea. When those charged particles paired off, the scattering that kept the fog thick diminished sharply. In a single cosmic instant, light that had been trapped at every turn could finally slip free. That freed light is what we still detect today as the cosmic microwave background, the CMB. It's a faint, nearly uniform glow that fills the night sky in every direction. You can't see it with your eyes. It bathes the universe at about 2.725 Kelvin, a whisper above absolute zero. But it's everywhere, and it carries a story older than anything made of stars. To grasp that story, picture a photon that was born at the moment of decoupling. It left on a journey that would last more than 13 billion years. The universe stretched while that photon traveled. Space itself acted like an invisible looper, lengthening the photon's wavelength. What started out in a much hotter, bluer part of the spectrum cooled with the cosmos, shifting into the microwave range that our detectors now measure. In human time, that travel feels unimaginable, but in cosmic terms, it's a message carried across the vastness of space and time. If you've ever looked at a false color map of the CMB, you've seen the universe's baby picture. At first glance, those maps are almost eerily smooth, mostly a uniform glow, but look closely and you'll find tiny ripples, temperature differences of just a few parts in 100,000. Those wrinkles are crucial. Each subtle hot spot or cold spot marks a place where the density of matter was just a touch higher or lower than the surrounding regions. Those slight overdensities were the seeds that gravity used to sculpt galaxies and clusters over billions of years. To make this feel personal, think back to your own childhood photos. Even the blurriest snapshot captures hints: a smile, a hand on a shoulder, the set of your parents' eyes, details that tell you more about the people in the picture than any caption could. The CMB is our universe's childhood photo. It's soft and slightly blurred, but if you're patient and careful in how you read it, every pattern is a clue about what the universe was made of, how fast it was expanding, and how structure first grew. When physicists and astronomers began to study the CMB in detail, they found more than just a pretty pattern. The ripples are arranged in a way that reveals the physics of the early universe. The way pressure and gravity set the primordial plasma ringing like a bell. Those sound waves in the early plasma, pressure waves pushed and pulled by photons and baryons, left their fingerprints in the angular size and relative heights of peaks in the CMB's power spectrum. From those fingerprints, we can measure the composition of the cosmos. About 5% ordinary matter, roughly 27% dark matter, and the rest, dark energy. We can estimate the universe's age and geometry and test whether the simplest inflationary models that describe the universe's earliest moments hold up. The story of how we learned this is almost as charming as the data itself. The CMB was first detected as a persistent radio noise by Arno Penzias and Robert Wilson in 1964. They thought at first it was just an annoying hiss in their antenna. When that hiss couldn't be explained away, theorists realized it matched the predictions for leftover radiation from an early hot universe. That discovery tied a neat ribbon on the Big Bang idea and opened a new window on cosmic history. Since then, instruments like COBE, WMAP, and Planck have taken increasingly precise portraits, each one sharper and more informative than the last. Those maps are measured with amazing subtlety. The temperature differences are tiny, roughly 1 part in 100,000, and the instruments must be extraordinarily stable and well calibrated. Observatories are placed on satellites far from the noisy environment of Earth's atmosphere, or in dry, high places on the ground to avoid contamination. Teams of people pore over the data, removing foreground emission from our own galaxy, separating microwave glow from dust, and extracting the pure CMB signal. The result is a cosmic tapestry, and the patterns are not random. They follow physical laws borne out in the math of early universe plasma dynamics. There's another layer to the CMB's message: polarization. When those very first photons last scattered off electrons, the scattering process left them weakly polarized in a way that depends on the motions in the plasma. Mapping the tiny polarization patterns, the so-called E modes and the hunt for B modes, gives us a different kind of fingerprint, one that can potentially reveal the presence of primordial gravitational waves or other exotic physics from the infant universe. Polarization measurements are harder and noisier to make, but they're an essential piece of the puzzle and a growing frontier in observational cosmology. All this is the product of a simple, magnificent idea: that light can act as a time machine. When you look out into space, you're not just seeing distant places, you're seeing things as they were. The CMB is the furthest of those images, a sphere we can picture around us where every direction intersects the same era, the moment the fog lifted. That's why we call it the surface of last scattering. It's the last time the photons interacted strongly with matter before streaming freely. Because the CMB is everywhere, it's a remarkably fair sample of the universe at that time. But it's not perfect. There are anomalies that still puzzle scientists. For example, a curious cold spot, larger than expected, or some unexpected alignments on the largest angular scales. These might be statistical flukes, or they might hint at new physics we don't yet understand. The beauty is that the CMB doesn't just provide answers, it refines the questions we ask about the cosmos. From a human perspective, what's magical is how intimate this ancient light feels. You could be sitting on your couch with a cup of coffee, and above the mundane clutter of daily life, there is an invisible glow that remembers the universe's first clear morning. Every microwave photon passing through your room has a pedigree that goes back to that 380,000-year-old moment, a time when the only structures that existed were minuscule imbalances in density. Those imbalances, over deep time, led to the galaxies that host the stars that forged the atoms in your body. So when instruments map that glow and reveal the tiny wrinkles, they're telling us where to look for the future and how to interpret the past. They tell us how the cosmos preferred to arrange itself, how sound and light danced in the first 100,000 years, and how those dances left marks that would amplify into galaxies, clusters, and the cosmic web. If you want a simple human image to carry with you, imagine stepping outside at dawn into a world that has always been a little hazy. Then imagine the haze lifts, the horizon sharpens, and for the first time, you can see the shape of the place you've always lived. The CMB is that clearing. It's the afterglow from the first clear morning anything anywhere ever saw. It fades into the cold microwave background, but its details are enough to tell a rich story about where we came from and how our cosmic neighborhood was born. And whenever you look up into a dark, starry night, remember, the distant, faint microwave hum around you is not noise or empty space. It's the quietest lighthouse imaginable, shining everywhere at once. It doesn't point you to a single place. It points you back to the beginning of structure, to the time when the universe first let light travel freely. That light has been traveling since before there were stars, and it still carries in its soft colors the fingerprints of the universe's first whispers. Think of placing a handful of dots on a stretchy fabric and then tugging the edges slowly. Each dot rolls away from every other dot, not because any of them decided to sprint, but because the fabric underneath them is stretching. That simple picture is the heart of how the universe expands. Galaxies aren't cosmic runners dashing through a pre-existing stage. They're like those dots, carried apart as the stage itself lengthens. What that means for us, practically and emotionally, is both comforting and oddly intimate. When we look at a distant galaxy, we're not watching it flee from us like a panicked animal. Instead, we're watching the space between us and it grow. And because space is stretching, every light wave it's sent toward us is stretched too. A photon that left a galaxy billions of years ago starts out with one color and arrives here with a redder one, its wavelength pulled thin by the widening distance. That reddening, redshift, is our cosmic yardstick. The farther away the galaxy, the faster it appears to be receding. Put simply, distance translates into apparent speed. That's Hubble's discovery standing quietly behind observations. More distant galaxies show larger redshifts. You might worry, this sounds like a speed limit violation. Doesn't that mean some galaxies are moving faster than light? That's the beautiful subtlety. Nothing locally outruns light. Special relativity, the rulebook for motion close to you, still applies in every small region of space. Imagine a tiny neighborhood like the room you're sitting in. Light still reigns as the fastest messenger across that room. The expansion changes the background, not the local rules. Over vast cosmic distances, the expansion of space can make the separation between two far apart points increase faster than light, without any object locally exceeding light speed. It's like 2 points painted on different parts of an inflating balloon. The distance along the balloon's surface increases, but the paint isn't sliding across the surface at superluminal speed. That same fabric analogy explains something else that always surprises people. There is no center to the expansion. Pulling the edges of a sheet moves every dot away from every other dot in a perfectly uniform way, no matter which dot you choose as your reference. From any galaxy's point of view, the rest of the universe appears to be rushing away. This isn't a universe where we occupy a privileged vantage point. It's a universe that grows everywhere. And yet, despite all that motion at the greatest scales, many things remain comfortably unchanged. Your coffee cup, the Earth, even our galaxy. These are held together by forces that beat the gentle stretching of space. Gravity and electromagnetism are obedient local landlords. They keep atoms, planets, and galaxies bound. Only when you look between clusters of galaxies, where gravity's grip loosens, does the expansion of space take the upper hand and carry systems apart. So your morning commute and the orbit of the moon are entirely immune to cosmic stretching. Now, think back to the very beginning, if you can. In the first sliver of a second after the Big Bang, something almost unimaginable happened. The universe underwent a stupendous, blisteringly quick swelling called inflation. It's helpful to picture a tiny patch of space, smaller than an atom, blown up in a heartbeat to astronomical size. That brief surge smoothed and stretched space, and it did something even more remarkable. It turned minute quantum jitters into the scaffolding for everything that followed. The tiniest fluctuations in density, born as quantum ripples, were magnified into the blueprint for galaxies, clusters, and the web of structure we see across the cosmos. Those ripples are visible today as faint irregularities in the cosmic microwave background, the afterglow of the early universe, and as the seeds from which galaxies grew. After that frenetic beginning, expansion settled into a more measured pace. For most of the universe's life, gravity, pulling things together, slowed the spread. Matter dominated, stars formed, and the cosmos cooled. But in our recent cosmic epoch, something subtle but profound has changed. Measurements of distant exploding stars, type Ia supernovae, revealed that the universe's expansion isn't slowing down anymore. It's accelerating. The cause is a mystery we call dark energy, a kind of pressure or property of space that works against gravity's pull and gently pushes the cosmos apart. Dark energy doesn't scream or shove. It's a quiet, pervasive influence, a persistent tendency of space to prefer expansion. That gradual acceleration reshapes the future in a way that's serene but inexorable. As space expands and the universe cools, galaxies that aren't gravitationally bound pull away from each other. Light from some of them will never reach us again. Their photons get stretched so much and the distances grow so fast that they slip forever beyond our cosmic horizon. But that's far off, measured in timescales far longer than the span of human history. For now, the universe's expansion is a slow, patient process, a cosmic inhalation and exhalation played out over billions of years. If you want a more human-scale metaphor, imagine the cosmos as a chest taking a long, gentle breath. In the active inflationary instant, that breath was a gasp. all lungs and adrenaline. Today, it's a slow relaxation, the chest letting out air, creating room inside. That room is crucial. As the universe expanded and cooled, conditions became hospitable for atoms to form, for clouds of gas to condense, and for the first stars to ignite. That patient opening of space gave time and territory for complexity to arise. Without that calm expansion, the dense, hot chaos of the early universe might never have settled into the forums where chemistry could begin and life much later could emerge. The observational evidence for all this is elegant and abundant. Edwin Hubble's original observations of galaxy redshifts made the case for expansion a century ago. The cosmic microwave background shows the imprint of ancient density variations, the fingerprints left by inflation's quantum seeds. Supernova surveys told us the expansion is speeding up now. Large galaxy surveys map out the cosmic web, the aftermath of those initial ripples. Together, these lines of evidence create a consistent story. A universe that began small was blown out quickly, then carried on expanding more gently, with a late-time acceleration driven by dark energy. It's okay not to crunch the equations to feel the wonder. Still, a few intuitive checkpoints are worth keeping in mind. First, expansion is not a force rushing galaxies away. It's the growth of distances. Second, local physics, atoms, planets, people, is not stretched along with the vast intergalactic distances. Third, the farther away a galaxy is, the faster its light appears to recede, and the more its light is reddened. Fourth, inflation amplified the tiniest quantum irregularities into the cosmic structure we now study. And finally, dark energy is the present-day driver, nudging cosmic expansion into acceleration. On a personal level, that perspective can change how you relate to the night sky. When you look up at the faint smudge of a distant galaxy, know that each photon that reached your eye has journeyed across an expanding ocean of space. That photon is a time capsule, stretched and softened, carrying with it the story of a universe that has grown and cooled since it left its home. We're not static observers watching a chaotic scatter of objects. We are part of the flow, co-moving with the expansion. The universe is not a dramatic sprint toward emptiness, so much as a wide, thoughtful making of room. There's something almost soothing in that image. The cosmos is patient. It expands to give itself the chance to cool, to settle, and to allow structures to form slowly over eons. From the explosive instant of inflation to the gentle pressure of dark energy today, expansion has been the primary rhythm of cosmic history. It has made space for stars to be born, for planets to coalesce, and for life to find a niche on one small world. So the next time you feel overwhelmed by the pace of life, imagine the universe's gentle expansion, not as an erasure, but as an opening. It's a process that, on grand scales, makes room for complexity, for history, for stories to emerge and be told. Galaxies drift apart, not in panic, but in a slow, orderly stretching of the fabric they sit on. And that calm expansion is, in a very real sense, the canvas on which everything we care about was painted. Most of the stuff that keeps the universe together doesn't sparkle. It doesn't catch your eye when you look up at the night sky. It doesn't hum or shine or cast a shadow in any of the ways we're used to. Yet its presence is written across everything that does glow. We call that unseen stuff dark matter. A quiet, persistent weight that tugs on stars, bends the path of light, and threads galaxies into the grand filamentary web of the cosmos. Think of a grove of tall trees. When you stand beneath them, you notice the trunks and leaves, the patterns of branches and the sun through the canopy. You don't see the tangled system of roots beneath your feet, but you know it's there because the trees stay upright no matter how the wind blows. Dark matter is that root system on a vastly larger scale. It's an invisible scaffold holding up everything luminous, galaxies, clusters, and the delicate filaments that lace the universe. We first began to suspect this hidden framework by watching how stars and galaxies move. In the 1970s, Vera Rubin and her colleagues measured the speeds at which stars orbit the centers of galaxies. If visible matter, the stars, gas, and dust, were all there was, the stars farther out would slow down, moving more slowly the further they get from the bright center. Instead, the rotation curve stayed unexpectedly flat. Stars on the outskirts were orbiting far too fast to be held only by the weight of the visible galaxy. The gravitational tug keeping them in orbit had to come from something else, something that didn't shine. That suspicion was reinforced by other, independent lines of evidence. Fritz Zwicky, much earlier in the 1930s, noticed galaxies inside massive clusters were moving too quickly for the clusters to stay bound, if only the visible galaxies supplied the gravity. Then there are the most elegant fingerprints of all, the way light itself bends. Einstein told us gravity warps space, and when a distant quasar or galaxy aligns with a massive object on the way to our telescopes, we see the light bent into arcs and rings. In many cases, the amount of bending is far greater than the visible mass can explain. Mapping that gravitational lensing reveals concentrations of mass where we don't see light. Clear, visual proof that something invisible is doing the heavy lifting. One of the most striking images comes from the Bullet Cluster, two galaxy clusters that collided. After the collision, X-ray observations show the hot gas, the visible ordinary matter, slowed and piled up at the center where the collision occurred. But gravitational lensing maps place most of the mass offset from that gas, aligned instead with the galaxies that sailed through. The simplest explanation is that the bulk of the mass is carried by a component that doesn't interact electromagnetically. It passed through the collision without slowing, just like ghostly roots that keep growing while the soil moves around them. That observation made it difficult to explain the data by tweaking gravity alone and gave dark matter a stronger footing. On even larger scales, the universe shows us a cosmic web, long filaments of galaxies and dark matter that surround enormous voids. Huge surveys of galaxies and the faint patterns in the cosmic microwave background, the afterglow of the Big Bang, both require a form of matter that clumps gravitationally but doesn't radiate. Simulations seeded with dark matter produce structures that look eerily like what we observe: web-like filaments, dense nodes where clusters assemble, and halos of dark material that cradle galaxies. Remove the dark matter, and the universe's large-scale picture starts to look wrong in ways we can measure. So what is this invisible scaffold made of? That's the gentle riddle we tell ourselves at night. The shorthand is particle, but that's not a tidy answer. Whatever it is, it barely talks to the particles that make up us: protons, electrons, photons. It doesn't soak up light or emit it. It doesn't make noise in ordinary detectors. If you, right now, reach through your hand, a cloud of most dark matter candidates would pass through your body without even noticing, as if your hand were an uninteresting breeze. That property, to be essentially collisionless with respect to ordinary matter, is what lets dark matter form extended halos that cradle galaxies, rather than condensing into bright, compact objects. Physicists have sketched several possibilities. One family of ideas involves WIMPs, weakly interacting massive particles. These would be heavy particles that feel gravity and a faint weak force, but not electromagnetism. They were appealing partly because of a cosmic coincidence. Particles with weak force interactions produced in the early universe could naturally give the amount of dark matter we infer today. Another idea is actions, ultralight particles that behave more like a wave than a particle on astronomical scales. There are models involving sterile neutrinos, which would be heavier cousins of the known neutrinos, but practically invisible otherwise. Some proposes machos, massive compact halo objects like black holes or brown dwarfs, as a potential explanation, but surveys looking for the telltale flicker as these objects lens background stars have shown they can only account for a small fraction of dark matter. And then there are hybrid or stranger ideas. Self-interacting dark matter that slightly collides with itself. Warm dark matter that would smooth out small-scale structure. And proposals emerging from attempts to quantize gravity or extend particle physics. But keep in mind, all of these are shapes of a possibility space, not confirmed answers. Decades of experiments have been probing and narrowing the options. Deep underground laboratories house crystal detectors cooled to near absolute zero, listening for the faintest kicks from a dark particle bumping a nucleus. Massive tanks of liquid xenon sit in shields of rock, searching for tiny flashes of light that could signal a dark matter interaction. Telescopes look for indirect signs, a characteristic spectrum of gamma rays from distant regions where dark matter particles might annihilate, or telltale X-ray lines hinting at a decaying sterile neutrino. Particle colliders smash protons together, looking for missing energy that might hint at particles we can't see directly, but can infer from energy balance. None of these efforts has yet produced a smoking gun. That silence is meaningful. It tells us many of the simplest, most obvious candidates are either not there or interact even more feebly than we expected. And yet the silence doesn't diminish the presence we infer from gravity. It sharpens the mystery, makes it more elegant and elusive. There's a soothing side to that elusiveness. It means the cosmic scaffold is stable, patient, and gentle. If dark matter were bright and busy, the night sky would look very different. Stars would collide more often, galaxies might not settle into graceful disks, and the formation of planetary systems, including the slow stitch of our own, could be far messier. Instead, dark matter forms extended halos around galaxies, a kind of slow embrace that shepherds gas toward the centers, where stars can form on long, steady timescales. Those halos can be lumpy on smaller scales too, hosting dwarf galaxies and satellite companions that testify to a hierarchical growth of structure. Larger systems assembling from smaller pieces, all guided by the silent gravity of dark mass. You can make this personal in a way that doesn't require equations. Imagine lying awake, looking up at your ceiling, tracing the pattern of a mobile or a chandelier. You see the shapes, the hanging lights, the shadows they make. Now imagine someone told you that invisible wires run through the ceiling, a network of threads you can't see but that hold everything in place. You'd probably feel a small, comforting shiver. Something unseen is carrying weight so the visible things don't fall. Dark matter is that network for the cosmos. When you look at a steady galaxy, when you see the Milky Way as a faint blur on a clear night, what you're really looking at is baryonic matter, stars and gas, arranged and guided by a much larger, invisible halo beneath it all. Your quiet gaze is made possible by those ghostly supports. There are also surprises in how this scaffold behaves. In simulations, dark matter forms dense, central regions of halos and a population of smaller subhalos, clumps that should host dwarf galaxies. But when we map the real sky, the number and brightness of observed dwarf galaxies around the Milky Way are fewer than the simplest simulations predict. That missing satellites problem could be a clue. Perhaps many small dark halos never lit up into star-forming galaxies because feedback processes like supernovae blew the gas away. Or perhaps dark matter itself behaves in a slightly warmer, smoother way than the coldest models assume. These mismatches are the breadcrumbs scientists follow, trying to learn whether dark matter is perfectly aloof or whether it has a whisper of self-interaction or warmth that changes small-scale structure. Another delicate piece of evidence comes from the cosmic microwave background, that faint afterglow of the Big Bang. The tiny ripples in that ancient light encode the amounts of normal matter, and dark energy. To get the pattern of hot and cold spots we see requires a significant fraction of dark matter. That's an anchor that ties the early universe to the cosmic web we see today, a continuity of influence that spans nearly 14 billion years. It's as if the roots were planted at the beginning and have been steadying the growth of everything since. Even as experiments probe deeper, the humility of the problem remains. There is a certain human comfort in mysteries that are mostly silent. They give us space to wonder, to build instruments, to collaborate across continents and decades. Deep underground, teams of scientists calibrate detectors with millimeter precision. At radio telescopes, colleagues tune receivers to listen for the whisper of axions converting to photons in magnetic fields. On satellites and in huge optical surveys, astronomers map billions of galaxies to trace the cosmic web in ever greater detail. The pursuit is slow, patient, and cumulative, much like the way dark matter quietly shapes the cosmos. So tonight, as you listen and let your thoughts drift, imagine the universe with its lights and its dark. Picture the visible galaxies like islands of lantern light, each resting on a vast, unlit sea of dark matter. The scaffolding is not frightening, it's nurturing. It is the calm architecture that permits stars to continue their long lives, planets to orbit, and life in at least one tiny place to awaken and look up and ask questions. We don't need to know the last detail to take comfort in the fact of the structure. Knowing that even the darkness has shape, that it organizes and cradles, is enough to let the mind settle. The galaxies you admire are not drifting away. They are held with a steady, invisible hand. That slow, patient gravity has been doing its work long before you were born, and will keep doing it long after this moment passes. For tonight, that is a beautiful thought. The cosmos, wide and mysterious, rests on a silent scaffold, and because of it, the lights we love continue to shine. So here's the quiet part. As space itself stretches, it doesn't just drift lazily along. It accelerates. There's no engine, no cosmic wind, no mysterious hand pushing galaxies on like soccer balls across a field. Instead, the expansion of the universe has a built-in tendency to speed up, a subtle bias in the fabric of space that gently insists on creating more room. We call that tendency dark energy. The phrase is a placeholder for a real observational fact. Something about the universe makes expansion accelerate. The words dark and energy help us talk about it, but they don't explain it. They mark a curiosity. To picture it, imagine you're in an enormous balloon shop, not blowing air into a balloon so it bursts outward, but letting a balloon sit and somehow stretch on its own. The material of the balloon slowly decides to make more surface for no external reason. That's odd, because everything we normally know, dust, gas, stars, light, becomes less dense as it spreads out. If you sprinkle a cup of sand across a table, the sand thins. Dark energy behaves differently. Its density appears to remain essentially constant even as space expands. So, as the universe grows and ordinary matter thins, the proportion of the cosmos dominated by this steady background pressure rises. Over cosmic time, it becomes the dominant influence on the big picture. You can also think of dark energy as the gentlest kind of pressure. In everyday life, pressure usually pushes outward. Here, the pressure has a strange twist because of how it interacts with gravity and space. In Einstein's equations, certain forms of pressure can lead to repulsive behavior on the largest scales. So, instead of clumping things together, this soft pressure works to pull regions apart. It's not violent. It's not dramatic. It's a slow, smooth acceleration, like the way a tide that you don't notice at first eventually reaches your ankles. That smoothness matters. Unlike a sudden shove that would scatter galaxies like leaves in a storm, dark energy simply nudges the expansion rate upward. Over a handful of billions of years, the effect is profound. Today, the galaxies nearest to us still fall into large groups and clusters under mutual gravity. But beyond those neighborhoods, the expansion dominates. Faraway galaxies recede. Their light is stretched, reddened, and weakened. Some of them are already moving away so fast that the light they emit now will never reach us at any time in the future. There are regions of space that are, for all practical purposes, permanently out of contact. Here's another way to picture what that means. The observable universe is not a sphere with a wall you could theoretically cross. It's more like a window defined by time. We can only see light that has had the time to travel to us since the Big Bang. If, because of dark energy, the space between here and some distant galaxy expands faster than light can traverse it, then no signal from that region will ever arrive. The limit of what we can observe is set by the combination of how far light has traveled and how the space it travels through has been stretching. The farther the stretchers, the dark energy, win out. The smaller our causal neighborhood becomes in a practical sense, even as the overall universe grows larger beyond comprehension. That fact can feel unsettling. A universe that keeps making more of itself while isolating its regions. But there is a gentle counterpoint. What you see in the night sky is complete for you. The map of galaxies and cosmic background photons that surround our patch of the universe is a perfectly framed window, the full show available on your timescale. Beyond that frame, maybe there are whole other collections of galaxies, stars being born and dying, civilizations flourishing and fading, all of it continuing without needing you to follow. It's a small, calming thought. The cosmos carries on, and you are not obligated to chase every distant point of light. Relating that to the human scale helps it land emotionally. Think about growing older and seeing friends move away. You can try to chase every relationship at every distance, but life has its own expansion. Priorities shift, energies thin. Acceptance doesn't mean resignation. It means recognizing the boundary of what you can influence and finding a kind of peace in the territory you occupy. The universe, in a sense, practices the same acceptance. Dark energy enforces a kind of cosmic mindfulness. The accessible patch is finite. The rest can proceed without you. That can be lonely if you insist it should be otherwise, but it can also be profoundly liberating. A practical consequence of dark energy's constancy is how it changes the arithmetic of dominance. Early on, radiation and then matter shaped the universe. When the cosmos was hot and dense, radiation's energy density dominated. As it cooled and matter clumped, gravity slowed expansion. But dark energy, if its density really stays nearly the same as space expands, becomes comparatively more important. The relative contribution of matter and radiation dwindles because their energy is diluted by expansion, while dark energy remains stubbornly present per unit volume. That's why we live in an era where its effects are visible and measurable. Astronomers inferred dark energy by watching distant exploding stars, type Ia supernovae, and realizing the expansion is accelerating, and later confirmed it with the cosmic microwave background and the distribution of galaxies. One useful number to have in your mind: the transition to dark energy domination happened only a few billion years before now. Given that the universe is about 13.8 billion years old, that means for most of cosmic history, gravity and matter set the pace. Only relatively recently in cosmic terms did this soft pressure become the prime mover on the largest scales. Which is to say, if you worry that dark energy is some sudden cataclysmic force, remember that it has been doing this gently for billions of years, gradually nudging the universe in a quieter direction. If we follow the logic forward, dark energy implies a future where distant galaxies fade from our view. Light reaching us gets stretched to ever longer wavelengths until it's effectively gone from the visible sky. In many trillions of years, the universe might be a lonely place observationally. Only the nearest gravitationally bound systems, our local group, then just the Milky Way and Andromeda merged, remain visible. The map of the cosmos shrinks until local structures are all that can be observed. From that future vantage point, civilizations might reconstruct a cosmology that looks very different because the distant evidence is gone. That thought is sobering, but it also highlights the significance of our current era. We have the rare privilege of observing a universe rich in structure and clues about its origin. For many people, that leads to a moral or philosophical reflection. If the cosmos is, by its nature, providing a local frame and letting the rest drift away, what should we do with the awareness we have now? One response is curiosity. Learn, observe, archive, send messages into space. Another response is tenderness. Appreciate the complete window of experience you already possess. The heavens you see are not incomplete because there's more beyond. They are perfectly sufficient for life, for meaning, for science. The accelerating universe invites both wonder and rest. I want to end this section with a simple scene you can take into your own life. tonight. Stand or sit wherever you most like to look up. Let the sky be enough. The stars you see, their arrangement, their light, the stories they contain, form a coherent world of its own. Remember that some lights are already beyond your reach in the technical sense, but that doesn't make the ones you can see any less luminous or less worthy of attention. The universe's soft pressure does not demand that you chase the unreachable. It gives you instead a beautifully framed, time-bound view that is uniquely yours to explore, cherish, and rest within. Pull back another step from the galaxies, another stitch in the fabric, and a striking pattern takes over. Instead of isolated islands of light, the universe arranges itself into a vast lace of matter. Long, wispy threads connecting bright knots with enormous dark swaths in between. This is the cosmic web, filaments that run for hundreds of millions of light years, meeting at dense clusters like beads on a string and leaving enormous voids where almost nothing luminous resides. Imagine standing outside everything and watching a faint fog of galaxies slowly sharpen, resolving into long, delicate strands, as though the universe had taken a paintbrush and begun to draw with the light of 1,000,000,000,000 suns. That image makes the mind click into a comforting register. There's an immediate, almost tactile recognition. Branches and crossings, junctions and highways, and people naturally reach for familiar comparisons. A neural network, a knitted shawl, the map of a river system. The resemblance is visual more than physical. Neurons and galaxies don't share the same forces or time scales, but the similarity matters emotionally. When you look at a map of the web and see those long connections and nodal hubs, it feels like a pattern your brain already knows how to live inside. The universe has arranged itself in a way that makes the mind feel at home. Behind that pattern are two simple facts: gravity and time. In the moments after the Big Bang, the universe wasn't uniform by an infinitesimal amount. Tiny ripples in density, fingerprints left by quantum fluctuations during inflation. Over cosmic time, gravity amplified those ripples. Dark matter, the invisible material that outweighs ordinary atoms by several times, provided the scaffolding. It clumped first because it felt gravity while not being held back by light or pressure, and ordinary baryonic gas followed, sliding into the valleys carved by dark matter. Where those valleys intersected, matter piled up into knots, the clusters we see today. Between them, long filaments remained, conduits where matter slowly drifts inward. And in the spaces where the ripples were initially less pronounced, the universe expanded a bit faster, leaving vast, cold voids. That's the physical story, but it's also a story written in geological time. Filaments grow and evolve across billions of years. Gas trickles along them, cools, and condenses into new stars. Galaxies riding these streams can merge gently when they arrive at a node, changing shape, collecting satellites, and sometimes igniting bursts of star formation. The pace is never frantic. Even the most dramatic collisions among galaxies, the collisions that create long tidal tails or feed central black holes, take hundreds of millions of years. The web is patience made manifest, a structure born from the steady, impartial pull of gravity acting over the longest spans we can imagine. We can see this pattern because of massive surveys and simulations. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing the filaments and voids that sketch the cosmic web. Computer simulations such as the Millennium, Illustris, and Eagle projects let us watch virtual universes grow inside a supercomputer, letting us see how dark matter halos merge and how gas streams along filaments to feed galaxies. In those simulations, the pattern is unmistakable. Threads span great distances, knots grow ever denser, and the empty regions become emptier. Observationally, we can even detect the diffuse gas in some filaments, the whisper of baryons between the galaxies. Using X-ray observations, the Sunyaev-Zeldovich effect, and absorption lines in the spectra of distant quasars. The web isn't just a pretty theoretical picture. It's a physical structure we can measure. If you've ever stared at a map of a city, searching for the easiest route between 2 points, you instinctively understand how the cosmic web functions. Filaments are like highways for matter. They guide gas and galaxies toward deeper gravitational wells. Nodes, the clusters, are urban centers piled high with galaxies, and voids are the parks or undeveloped land between neighborhoods, vast and quiet. This analogy goes beyond a simple metaphor. Just as people congregate where resources, jobs, and transport intersect, matter in the universe is shepherded where gravitational potentials align. The difference is scale and time scale. Human cities change in decades, whereas cosmic cities accrete mass over billions of years. That difference matters because it gives the web a quality that feels almost philosophical. Stillness, not inactivity, rather a slow, deliberate ordering. There is movement, gas flowing, galaxies orbiting, collisions happening, but those changes fold into a longer narrative in which the emergent pattern endures. The cosmic web is a record of the universe's patience, the result of simple physical laws operating without hurry until complexity arises. It's a good story to keep in mind when life feels rushed or fragmentary. When your days are noisy and your attention is scattered, looking at the web can be a quieting metaphor. Small, steady forces, applied consistently, make patterns. Make it personal for a moment. Think of your life as a tiny point of light somewhere along one of those filaments. You're not alone. You're part of a network of relationships, routines, places, and projects that guide the flow of energy into your life. Some of those connections are dense and bright, like clusters. These are the relationships and duties that demand your attention. Others are looser filaments, acquaintances, interest groups, or passions that bring subtle richness over time. And there are voids, stretches of quiet, where the absence of activity creates space for something different to happen. It's tempting to equate activity with progress, but the cosmic web suggests another truth. Order and growth don't require frantic motion. They require the right channels, maintained over time. There's also humility in the web's scale. Every galaxy we can resolve is a bright node in an almost incomprehensible lace. Each of our personal strands, relationships, work, daily habits, seems essential from the inside. From the outside, people are points among points. That viewpoint can be freeing. It doesn't make your choices meaningless. It reminds you that everything operates within larger patterns and timescales. If you're wrestling with a slow project, a long-term relationship, or the slog of changing a habit, imagine the filament, A slow, steady flow will eventually deliver results. You don't need constant urgency. You need persistent direction and an awareness of the channels that feed you. We can also learn something practical from the web's architecture. Connections matter more than intensity. A filament doesn't have to be a blinding flood of matter to shape a galaxy. Over time, small but persistent flows accumulate. In human terms, that looks like small habits, modest acts of kindness, a weekly check-in with someone you care about. These aren't flashy, but they are the structural threads that support a flourishing life. Likewise, nodes, our networks of close friends and colleagues, grow their own mini ecosystems. They reshape us not by sudden upheaval, but by the aggregated, gentle persistence of attention and presence. There are scientific surprises too. Not all filaments are the same. Some are relatively thin and quiet, barely detectable except in specialized observations. Others are massive, carrying hot gas that glows in X-rays. These are the busiest highways of the universe, the regions most actively building galaxies. The warm, hot intergalactic medium, the WHM, is thought to hide a large fraction of the universe's ordinary matter, diffused through filaments and hard to see. Detecting it requires clever techniques, stacking many observations to tease out faint signals, or tracing the imprint of filament gas on background quasar light. Those methods are like discovering a faint network of irrigation pipes beneath a landscape. Pipes you can't see from street level, but whose presence explains why certain fields stay green. Another lesson comes from the nodes themselves. Galaxy clusters are the largest gravitationally bound structures in the universe, and they are laboratories for slow transformation. Inside a cluster, galaxies can be stripped of their gas by the intra-cluster medium, a hot plasma that acts like a cosmic wind. Over time, that process shuts down star formation in cluster galaxies, turning them into red, quieter systems. Mergers inside clusters can be graceful and slow, sometimes nudging galaxies into new shapes, but seldom producing the sort of cataclysmic fireworks we might imagine from a simplistic collision metaphor. The drama of clusters is largely the drama of cumulative patient change. We should also mention the emptiness, the voids. They are not simply nothing. They have their own subtle dynamics. Because they are underdense, they expand slightly faster than average and can be quieter environments where galaxies evolve differently. Some astronomers wonder whether life-bearing planets would be more or less common in void galaxies. A speculative question, but it highlights how the cosmic web's architecture shapes everything within it, from the largest clusters down to the internal histories of individual galaxies. If you're someone who needs an image to carry you through difficult chapters, let the web be that image. Picture your life as a point along a filament. You have neighbors, some bright and constant, others ephemeral. Material, opportunities, resources, knowledge flows toward the denser regions, sometimes passing you by, sometimes sweeping you along. You can't control the whole structure, but you can attend to the local channels, maintain a few steady connections, feed them thoughtfully, let them feed you back. You'll be surprised how much can happen through low-level persistence, rather than high-intensity bursts. This perspective doesn't diminish the value of urgency when it's necessary. There are moments when speed matters. But the cosmic web's dominant lesson is the power of sustained directional influence. Gravity is a simple law, but applied over eons, it produces staggering complexity. Your own life can follow the same principle. Choose a simple rule. Show up, read a little, practice, check in, and let years do some of the work. That's how filaments build galaxies. Finally, allow yourself the comfort of cosmic stillness. Look up at the pattern of the stars, at the smeared glow of the Milky Way arching overhead, and imagine that, far beyond our sight, long filaments connect clusters in a quiet geometry of motion. The web is not a frantic arrangement, but an elegant, patient design. In a culture that often prizes speed and immediacy, the universe offers a different model. Order arrives by the accumulation of small pulls, every one predictable, none hurried. When you feel scattered, that image, threads holding their shape without rush, can be a kind of anchor. So next time life feels fractious, try this. Breathe, name one small thing you can sustain, and picture the filament behind it. Visualize your effort flowing along a gentle channel, joining others, and eventually feeding something larger. In the end, the cosmic web is both a map and a metaphor, an enormous, beautiful scaffold that reminds us how complex structure can grow out of simple rules and long, quiet time. We are tiny lights on those threads, and our small persistences matter more than we often realize. There was a time when the universe was a dark, cooling place. No twinkling lights to mark the hours, only a slow spreading of shadow after the Big Bang's first glow. Imagine standing in a forest at midnight, pitch black except for the faint outline of trees. Then someone strikes a match. That tiny flare changes everything within its reach. The first stars were those matches, pockets of gas where gravity finally beat the long odds and squeezed matter hot enough to ignite nuclear fusion. How did that happen? After the universe cooled enough for protons and electrons to combine into neutral hydrogen, the radiation that had been everywhere thinned and the cosmic fog lifted. Gravity kept tugging, and small fluctuations in density, regions just a little bit denser than their surroundings, began to grow. These were not neat, syringe-shaped clumps, but messy, chaotic knots of hydrogen and helium. In those knots, gravity pulled gas inward, compressing and heating it. If a clump reached the right combination of mass and temperature, the pressure trying to push back could no longer win. The gas collapsed, and in the center of that collapse, temperatures climbed until hydrogen atoms could begin to fuse. A star was born. But these first stars were born into a very different universe than the one we know. They formed from gas containing only hydrogen and helium, the elements made in the Big Bang, and almost none of the heavier elements astronomers call metals. Metals, in astronomical language, include carbon, oxygen, iron, everything beyond helium. Those heavier elements are efficient at radiating away heat, which lets collapsing gas fragment into many small pieces. Without them, the gas had to rely on the weaker cooling channels available to primordial gas, primarily molecular hydrogen. The result? Collapsing clouds stayed comparatively warm and therefore tended to form far more massive stars than we see forming today. When we try to picture these pioneers, we often talk about them as titans. Many models predict they were tens to perhaps hundreds of times the mass of our sun. Some theoretical work even suggests some could have been several hundred solar masses. Big mass means intense gravity in the core, which means extraordinarily high pressures and temperatures, which in turn produces ferocious rates of nuclear burning. Those stars shone with blinding intensity, but they paid for that brilliance with brevity. Instead of living for billions of years like the sun, they lived for mere millions, sometimes for only a few million years, and then died in dramatic ways. Their deaths were the turning points. Massive first stars could explode as supernovae that were not merely brilliant fireworks, but the universe's first forges. In the hearts of these stars, and in the violent conditions of their deaths, lighter elements fused into heavier ones, helium into carbon, carbon into oxygen, onward to silicon and iron in the most extreme cases. Some of the very most massive stars may have ended in pair instability supernovae, explosions so complete they left nothing behind and scattered enormous amounts of newly formed elements into the surrounding cosmos. Other massive stars collapse to form black holes, sometimes after ejecting large portions of their enriched outer layers. Either way, those explosions seeded the surrounding gas with the first metals. Think about that for a moment. Every carbon atom in the air you breathe, every iron atom in your blood, all those building blocks of planets and life, they owe their first existence to these vanished pioneers. The first stars didn't live long, but what they released into space changed the rules of star formation itself. Once a region of gas contained even trace amounts of carbon, oxygen, or other metals, it could cool far more efficiently. Cooler gas fragments into many smaller lumps, allowing the next generations of stars to include low-mass stars with lifetimes long enough to survive to the present day. In other words, the first stars were the spark that made future suns, and eventually planets and life, possible. We haven't actually seen these first lights directly. They formed so early, so far away, and so briefly that their individual glows are drowned out by time and distance. The expanding universe redshifts their light into wavelengths that are difficult to detect, and intervening gas absorbs much of the high-energy radiation they produced. But absence of sight isn't absence of evidence. We read their fingerprints in several ways. One of the clearest clues comes from the chemical compositions of extremely old stars that still survive today. There are stars in our galaxy's halo and in small satellite dwarf galaxies that show remarkably low amounts of heavy elements. They're the archaeological artifacts of the early universe. Some of these metal-poor stars have odd abundance patterns that match the theoretical yields expected from the supernovae of very massive, metal-free progenitors. For example, some old stars are unusually rich in carbon relative to iron. That can be explained if they formed from gas polluted by a specific kind of early supernova. These stellar fossils act like time capsules, preserving the chemical signatures of those first explosive events. We also see evidence in the diffuse gas between galaxies. Surveys of distant quasars reveal absorption lines in their spectra, where intervening gas clouds imprint signatures of elements like carbon, silicon, and oxygen, even at very early cosmic times. Those metals could only have come from stars. The obvious culprits are the universe's first generations of stellar explosions distributing enriched material into the intergalactic medium. The patchy pattern of metallicity, where some regions are enriched and others remain pristine, tells a story of local bursts of enrichment followed by mixing and diffusion over cosmic times. And then there's the grander scale footprint, reionization. The early universe began neutral, but at some point the hydrogen became ionized again, a process driven largely by the ultraviolet radiation from early stars and possibly growing black holes. The timeline for reionization, constrained by observations of the microwave background and distant quasars, suggests that those early stars played a substantial role in bathing the universe, in ionizing photons and reshaping the state of the intergalactic medium. That epoch, the universe shedding its neutral cloak, is directly tied to the emergence of the first luminous objects. What about the question of black holes? Some of the first stars, with their huge masses, likely left behind black hole remnants. These early black holes, if they merged and accreted material efficiently, might have been the seeds for the supermassive black holes we observe at the centers of galaxies. How a billion solar mass black hole could exist so quickly in the infant universe is still an open puzzle, and the first stars are a leading piece of that puzzle. All of this gives us a picture, but one with tantalizing blanks. Recently, telescopes like Hubble, ground-based observatories, and now JWST have pushed deeper into cosmic time than ever before. Astronomers hope to detect the indirect signatures of population 3 stars, unusual emission lines, clusters of extremely hot, metal-free stars creating distinctive helium emission, or even the integrated light of early star-forming galaxies showing very hard ultraviolet spectra. The data are messy and ambiguous, but the search is on. Each new observation narrows possibilities and sometimes surprises us, nudging theory into new territory. It helps to keep the human, personal angle front and center. When you look at a starry sky tonight, you're gazing at the later chapters of a story that began with those first fires. The light from a distant star might have traces of elements whose first atoms were hammered into place by a vanished giant that lived for a few million years and was gone. Every teaspoon of soil, every breath of air, every molecule in your body contains atoms older than the Earth itself, ultimately forged in stars that lived and died when the universe was still very young. That deep continuity is almost hard to hold in the mind. Your chemistry, literally, carries the handiwork of those earliest explosions. There's also a communal aspect to this story. Think of a campsite. A single flame brings warmth, but more importantly, it becomes a focal point. People gather around it, tell stories, pass tools and knowledge, and then wander off with new ideas. The first stars did much the same for the cosmos. They created the conditions for chemistry to become richer, for gas clouds to fragment into new kinds of stars, for galaxies to begin their complex growth. They were the first catalysts for cosmic evolution, creating the environment in which complexity, from planets to biology, could later arise. Finally, there's a quiet beauty in their absence. The fact that we haven't seen them directly doesn't lessen their reality. Instead, it makes their traces more precious. We are detectives reading the faint smudges they left on the fabric of the universe. Peculiar element ratios in ancient stars, the metals measured in wisps of intergalactic gas, the timing of reionization, the distribution of early galaxies. Together, these clues allow us to reconstruct the lives of stars we'll never meet, and to appreciate that the warmth we feel, at a human level, in the carbon in our cells or the iron in our blood, began with those first brief lights. So the next time you feel the sun on your face or smell smoke from a distant bonfire, let that simple sensation connect you to a far older story. The campfires we light now and the first fires of the cosmos are separated by eons and scales beyond imagining. But they share a role: to change the darkness, to forge what comes next, and to give those who follow the chance to carry on. The glow is gone, but the universe still carries their work. In the atoms around us and in the structure of every galaxy. They rarely live truly alone. Out in the vastness, galaxies are social creatures, not in the chatty, instantaneous way we are, but in a slow, patient, gravitational way. Picture a neighborhood where the residents move so slowly that a conversation can take billions of years. They circle, they pass, they reach out with long, gauzy arms of stars and gas, and sometimes two of them decide to walk together. When two galaxies of similar size encounter one another, it's not a crash like two cars on a highway. Stars are tiny, lonely islands separated by seas of empty space. Most stars in those galaxies will drift past each other without ever meeting. The real action happens in gravity's language. Tides and orbits and the slow redrafting of shapes. Giant spirals reach and stretch under the pull of their companion. Arms that once traced neat winding patterns become braided and flung out into space, forming those spectacular tidal tails we see in deep images. Streams of stars trace the past lives of small galaxies torn apart like ribbons left behind on a long walk. Think about the antennae galaxies, two spirals tangled in the throes of such a meeting. Their arms stream outward in luminous plumes, like hair pulled into a braid. Or look at the long, ghostly tidal streams around our own galaxy, remnants of dwarf galaxies that wandered too close and were gradually unstitched. These features tell a story, not of explosive collision, but of patient unmaking and remaking. A slow conversation written in starlight. What's really doing the talking is gravity acting over and over again. As two galaxies approach, their dark matter halos, those vast, invisible cocoons that dominate the mass of each system, begin to overlap. A halo isn't something you can see. It's the invisible weight that holds a galaxy together. When halos touch, you don't feel a jolt. You feel a pull. The galaxies start to tug on each other's outer stars and gas. Orbits stretch. Some stars are sent on new paths that loop far out into space. Others are nudged inward. This tidal stretching is like the ocean's tides, only on a scale so enormous that time itself dilates. Tidal features grow and fade across millions and billions of years. There's another, quieter mechanism at work called dynamical friction. It's not a force in the everyday sense, but an effect. As a galaxy moves through the halo and stellar sea of another, it creates a wake, a slightly denser region behind it, and that wake tugs back, slowly robbing the galaxy of momentum. Over immense times, that loss of orbital energy draws the two systems closer, turning a passing encounter into a lasting union. This is how two grand spirals, after swirling around one another and shedding arms and halo matter, can eventually settle into a single, more rounded shape. When two spirals of comparable mass finally merge, their ordered disc-like motions scramble. The graceful, coherent rotation that gives a spiral its arms breaks down as stars are scattered into new orbits. The result is often a rounded, smooth galaxy. what astronomers call an elliptical. It's not obliteration, it's reshuffling. The stars don't disappear. They simply swap their orderly dance for a new, more random choreography. The galaxy becomes a slower, more stately object, its light softened and redistributed. That transformation is sometimes dramatic, accompanied by bright bursts of star formation when clouds of gas collide and compress, and sometimes more subtle, the quiet settling of orbits over time. And this cosmic quiet house, where stars seldom bump into one another, holds another secret. Gas behaves differently from stars. When two gas-rich spirals meet, the clouds of hydrogen and other material can slam into each other, compressing and igniting waves of new stars. These starbursts can light up the central regions like 1,000 fireworks, and they can also funnel material toward the centers of the galaxies, feeding their supermassive black holes. For a time, a merging system can become extraordinarily bright, even outshining whole galaxies, as the central black holes flare up as quasars. It's a kind of dramatic punctuation in an otherwise languid conversation. Closer to home, our Milky Way is already in the early stages of such a story. The Andromeda Galaxy, and we are approaching each other at roughly 100 kilometers per second, a speed that sounds enormous until you remember the distances involved. Andromeda sits about 2.5 million light-years away now, but gravitationally, the handshake has begun. Their halos reach out far beyond the bright spiral disks, and those halos are starting to overlap with ours. It's as if two people standing far apart have extended their arms, and their sleeves are just starting to brush. You wouldn't feel that touch, but it changes the way each moves. In roughly 4 billion years, our two galaxies will begin a more intimate dance. Over the next few billion after that, their orbits will tighten. They'll swing through one another, pull out long tidal arms, and eventually settle down into a merged remnant. The galaxy some astronomers already nickname Milkomeda. Will our sun be thrown out into lonely, distant suburbs of that new galaxy? Will planetary orbits be disrupted? Most likely, the solar system will survive the encounter intact, but its address in the galactic map may change. The deeper truth is that this is not cosmic annihilation, it's reorganization. The stars, the gas, the dark matter, all the pieces are simply being relabeled and reassembled. They become part of a new home. If the scale of these processes feels overwhelming, shrink the picture down. Imagine two bright swirls on a park pond, each one representing a city of people. At first they skirt past each other, then they draw closer, their edges brushing, then stretching into filaments of shared stories. Over many afternoons they begin to circle together, sharing parts of their neighborhoods, swapping stray pets, eventually merging their communities into one larger, quieter town. The drama is in the choosing. Two bright swirls gradually deciding to share a sky, taking a very long walk together until they become one. There's tenderness in that image. Even where distances are measured in millions of light years, companionship finds a way to exist. Galaxies exchange material, stars, gas, even globular clusters, like neighbors borrowing tools over a fence. Small satellite galaxies orbit their larger hosts and slowly give up their stars to tidal streams, becoming ghostly filaments that wrap around the larger galaxy's halo. The Sagittarius dwarf galaxy is a real example of this ongoing theft. It's been steadily stripped apart as it circles the Milky Way, leaving a long stream of its former self wrapped around our galaxy like the remains of a trail. And because galaxies gather in groups and clusters, some are merely passing through while others are bound for eventual mergers. In dense clusters, interactions can be fast and violent. Galaxies can be stripped of their gas by the hot intracluster medium, or they can be torqued and spun by multiple, rapid encounters. But even there, the ultimate language remains the same: gravity shaping and reshaping, patient and inexorable. That patience can be poetic. Conversations between galaxies take place on timescales that dwarf human lifespans. For us, an encounter that takes billions of years is almost like a relationship that never quite reaches its climax. Yet, the fingerprints are left. Tidal tails, shells, streams, rings, and warped disks are the fossil record of past interactions. When astronomers look at deep images of the sky, they're reading the slow letters galaxies have written to each other over cosmic time. Each tidal stream is a sentence. Each ring of stars, a paragraph. Each merged elliptical, the closing chapter of a long story. And there's an intimacy to the whole process that's easy to forget when you reduce galaxies to numbers and graphs. Think about what it means for two systems to touch halos, to have their invisible envelopes overlap so that the motion of one is subtly altered by the presence of the other. It's the kind of proximity we can relate to. Neighbors who know, without a word, when the other is home. Friends whose lives change because of a single, shared cup of coffee. The scales are different, but the feeling, the gentle rearrangement that happens when two lives come close, is not. The night sky, when you look up, feels quiet and constant, but it holds these conversations in slow motion. The stars you see are part of a galaxy that has been shaped by countless such interactions. Our own ancestry includes small incursions and mergers that built the Milky Way's halo and thick disk. Every smooth, rounded elliptical we see in the depths of space likely tells a story of two once spiral neighbors who decided to merge. And in time, our own story will join theirs. So next time you stand beneath the stars, try to feel that hush of geological patience in the universe. Galaxies are not solitary islands. They are communities moving through a vast, shared landscape. They meet, they trade, they tug on one another's edges, and slowly, over epochs that outlast civilizations, they decide to take a long walk together. It's not a violent end, it's a transformation, an elegy and a beginning at once. Two bright swirls, choosing to share a sky until there's only one. Imagine for a second that space is not an empty stage, but a flexible fabric, something you can press your palm into and leave a little dent. That's the picture Einstein gave us. Mass tells space how to curve, and curved space tells everything else how to move. For planets and stars, that means orbits. For light, which always prefers to go straight, it means straight in the sense of the shortest path through curved geometry. In other words, light takes the scenic route. Picture driving through the countryside and choosing a winding back road because it's prettier. The distance you travel might be a little longer, the view different. Maybe you even arrive a few minutes later. When a massive object, a galaxy or a cluster of galaxies, sits between a distant light source and our telescopes, the path photons take can curve around that mass. To us, that detour can stretch and magnify the background light, turning faint, distant objects into bright, visible guests at our window. What you actually see can be astonishing. A single galaxy directly behind a massive cluster can be smeared into long, luminous arcs. Sometimes those arcs close into perfect circles. Those are the mesmerizing Einstein rings, where alignment is just right, and the geometry produces a symmetrical halo of light. Other times, a single point source like a quasar fragments into multiple images, identical copies of the same object scattered across the sky. The famous Einstein cross is one dramatic example. One quasar, 4 bright images arranged like a jewel on a backdrop of a lensing galaxy. There's a quiet magic to this. The universe becomes a cooperative host, bending light so we can meet things we otherwise couldn't see. Remote galaxies that would be invisible because they're too faint get magnified into view. Individual stars in other galaxies, stars so distant that even Hubble couldn't normally resolve them, have been briefly spotlighted when a lens acts like a cosmic magnifying glass. Think of that glass you keep in a drawer. Some parts slightly thicker, some thinner. Put it over a photograph and the picture underneath is still the same. But the shapes shift, the brightness changes, details stretch. That's lensing, geometry remixing light without changing the source itself. One of the most cinematic consequences of this geometry is time delay. Photons from the same event travel along different curved routes around the lens, and those routes aren't identical. They differ in length, and the curvature of space-time along each path changes the travel time. The result is a kind of natural replay system, the same explosion, the same flicker, arriving multiple times at different moments. Astronomers actually watched this happen with a supernova nicknamed Refsdal. The exploding star's light reached us in multiple images separated by weeks to months because the cluster that lensed it offered several distinct scenic routes. It was like watching the same film scene appear in different theater screens at staggered times, a cosmic production with intentional delays. That delay is more than a neat trick. It's useful. By measuring how long the light takes to arrive through each path, and by modeling the curvature responsible for that delay, astronomers can extract the combination of distances and mass distribution that produced it. In practice, time delay measurements are one of the ways we can pin down the universe's expansion rate, the Hubble constant, independent of other methods. It's like using the arrival times of echoes to infer the size of a canyon, except the canyon is the gravitational field of a galaxy cluster, and the echoes are the light of a supernova. Lensing is also a very direct scale for mass. Light bends in response to the total gravitational pull it passes, and gravity cares about everything that has mass or energy. That means dark matter, which we cannot see because it emits no light, nonetheless leaves a fingerprint on the paths photons take. By mapping how dramatically background galaxies are warped, by measuring the shape and orientation of those arcs and smudges, astronomers can reconstruct the invisible scaffold of dark matter in and around galaxies and clusters. It's a kind of cosmic weighing scale. The stronger the distortion, the more mass is there to bend space. There are different strengths of this effect, and each gives different kinds of information. Strong lensing is the dramatic stuff. Arcs, multiple images, Einstein rings. Those events are relatively rare because they require a close alignment of source, lens, and observer. But when they happen, they provide crisp, detailed constraints on the mass distribution in the lens. Weak lensing is subtler. Individual background galaxies show only a slight, statistical shear in their shapes, a tiny stretching that you can't trust from a single galaxy because galaxies come in their own shapes anyway. But look across thousands or millions of galaxies and the pattern emerges. Those small, coherent distortions let us map mass over huge swaths of the sky, revealing the cosmic web of dark matter that underpins structure formation. There's also microlensing. When a single star or planet in a lensing galaxy passes precisely in front of a background source, the magnification can spike and then fade on timescales of days to weeks. That effect has unearthed extrasolar planets and exposed otherwise invisible features in distant stars. It's a reminder that lensing works at many scales, from whole clusters down to individual stellar masses. If you want a mental picture that sticks, go back to the glass over photo idea, but add motion. Imagine laying a slightly warped, uneven piece of glass over a detailed map. From a distance, the map looks familiar, but when you tilt the glass or slide it around, lines bend, landmarks stretch, new pathways appear to connect places. Now imagine the light from the map taking different tracks under that warped glass. Some paths are quick and direct. Others curve around the thick parts and take longer. Pull away the glass and some features are magnified, some repeated. And by carefully studying those distortions, you could infer exactly how the glass is shaped, even if you can't touch it. Astronomers do the same. The sky is the map, gravity is the glass, and light is the traveler being guided by invisible contours. On a more personal note, when I first saw the Hubble images of lensed galaxies, those luminous arcs draped around a dim cluster core, it felt like watching a secret letter pressed against a window, revealed in moments of luck and geometry. There's an intimacy to it. You realize that the universe isn't indifferent. In its own way, it steps in to help observant spectators. Because of lensing, telescopes become more than devices that collect light. They become partners in a slow, gravitational collaboration that stretches across billions of years. Gravitational lensing has practical consequences beyond making pretty pictures. It has helped us spot some of the earliest galaxies, magnified enough to study their spectra, their star formation, their chemical compositions. It allowed astronomers to detect a star nicknamed Icarus, a single blue supergiant at a redshift that normally would be far too distant to resolve, thanks to a temporary magnification from microlensing. Lensing is how we catch glimpses of the universe's infancy, the whispered first generations of stars and galaxies, by amplifying their light into audible signals. It also challenges and refines our models. When lens maps don't match the luminous matter, when the distribution of mass inferred from lensing differs from the distribution of stars and gas, that mismatch is the strongest evidence we have for dark matter's presence and behavior. By comparing lensing maps with simulations that include dark matter, astrophysicists test theories of how structure forms, how dark matter clusters, and even whether our ideas about gravity themselves need tweaking. Every arc and ring is a data point in an argument about the universe's makeup. And because lensing is fundamentally geometric, it interacts with cosmology. The bending angle depends on distances between observer, lens, and source. So precise lensing measurements can inform the cosmic distance ladder. Time delays in multiple images, as I mentioned, offer a pathway to measuring the expansion rate of the universe without relying on local calibrators or the cosmic microwave background alone. That makes lensing both a microscope and a clock. It zooms in on small details and measures delays that tick off cosmic time. Of course, interpreting lensing signals is not trivial. You need good images, careful models, and an understanding of the lensing mass's complexity. Clusters are messy. Galaxies within them, hot gas and dark matter halos add up in non-trivial ways. Astronomers use lens modeling software, multiple wavelength data, and sometimes even machine learning to tease out the underlying mass distribution. But the payoff is huge. Maps of dark matter that would otherwise be invisible and snapshots of the universe's oldest lights. So next time you see a photograph of a galaxy cluster adorned with golden arcs, or a ring that seems too perfect to be anything but art, remember you're looking at geometry doing diplomacy. Gravity is subtly rewriting lines of sight so that faraway sources can speak more loudly. Light takes the scenic route, our instruments listen, and we read the story left behind in bent paths and delayed arrivals. The universe, in its quiet generosity, lets us piece together those stories, turning detours into discoveries. Pause for a moment and picture gravity not as a force pulling you toward a planet, but as a direction that chooses where every path leads. Near an ordinary star, you can step away, climb up, sail outward. Near a black hole, every path bends inward so thoroughly that, once you get close enough, moving inward is always the easier route. That boundary, the event horizon, is where the geometry of space and time tilts until out is effectively erased. At the horizon itself, something strange happens to light. Light isn't simply swallowed like dust. Photons can circle, they can be trapped in tight, looping orbits, and any little nudge can send them inward where they vanish from the outside universe. There is a critical surface just outside the horizon called the photon sphere, where light can, for a fleeting moment, circle the black hole. That behavior is the reason we can't actually see the hole. Light isn't coming from inside, but everything around it shouts its presence. What we do see are the fingerprints of what gathers and fights the gravity. Gas spirals inward, falling faster and rubbing against itself until it heats to incredible temperatures and glows across the spectrum. Visible, ultraviolet, X-rays. From the side, that glowing gas can appear as a smeared, almost painterly ring. From some angles, narrow jets shoot out perpendicular to the disk, corkscrewing particles away at near-light speed along magnetic field lines. Whole stars, tiny against that pull, get caught in tight, whip-like orbits that trace out the black hole's mass like beads on a string. Make it personal. Imagine watching this from a safe distance, a telescope between your eyes and the void. To you, things near the hole are moving strangely, not just fast but stretched. Time itself acts differently. Clocks down in the gravity's well tick more slowly than clocks far away. If some doomed parcel of gas were circling close to the edge, a minute in that gas's world could be watched from Earth as years of slow fade and reddening. That's not just a metaphor, it's a consequence of general relativity. To the traveler falling in, time feels normal. To you, watching from the light years, their motion slackens, reddens, and asymptotically fades into the dark. There are black holes born in violence, and others that grow patiently in the centers of galaxies. A massive star ends its fuel-burning life and collapses. If it's massive enough, nothing holds back the squeeze. The star becomes a stellar mass black hole, compact and intense, often found in binary systems where a companion star spills matter into its hungry neighbor. But then, there are the Leviathans, supermassive black holes, millions to billions of times the mass of our Sun, sitting like slow, steady anchors at the hearts of galaxies. They grew over time, swallowing gas, merging with other black holes, and quietly influencing the dance of stars around them. We learned to infer black holes long before we could give them a picture. For decades, they were elegant answers written only in equations, solutions to Einstein's field equations, places where predictions grew extreme and beautiful. Then, in 2019, an idea went from math and models to a real, grainy photograph. A planet-sized array of telescopes, the Event Horizon Telescope, stitched together signals from across Earth to create enough resolving power to see the silhouette of a black hole in the galaxy M87. The result? A bright, asymmetric ring surrounding a dark center, the shadow cast by the event horizon against glowing matter. It was a moment when abstraction became shape, when a concept we'd only ever imagined acquired edges and texture. And yet, despite the drama, there is a kind of calm to them. The word hole sounds abrupt, even violent, a maw, an abyss. But look longer. Black holes tidy. They take chaotic, sprawling gas and sculpt it into a thin, radiant disk. They channel motion into focused jets that ferry energy away. They are, in that sense, cosmic janitors, converting messy, high-energy chaos into ordered, cooler quiet over time. Not all black holes are ravenous. Many are quiescent, quietly influencing their neighborhoods without fireworks. If you could stand somewhere safe and listen with an instrument that hears gravity and light together, you'd sense a gentle, steady influence rather than constant violence. There's another twist that deepens the quiet. Black holes are not eternal prisons. Quantum theory adds a slow leak to their story. Near an event horizon, quantum fluctuations can create particle-antiparticle pairs. Occasionally one falls in and the other escapes, and the result is a faint thermal glow known as Hawking radiation. For astrophysical black holes, this radiation is unimaginably weak, a whisper against the cosmic background, and for supermassive black holes, it would take far longer than the current age of the universe to matter. But it changes the narrative profoundly. Even the darkest, most final-looking objects can, given time measured in unimaginable spans, lose heat grain by grain and fade back into the night. We can also feel the presence of black holes in precise, human ways. Centering on our own galaxy, observations of stars living close to Sagittarius A, stars called S-stars, let astronomers watch gravity in action. One star, named S2, swings in a fierce, elliptical orbit whose speed and trajectory allow us to weigh the invisible central mass. Those stellar orbits are not abstractions. They are clocks and probes. They tell us, in the language of motion, that something compact and massive sits unseen at the center. And when that something exists, it shapes the lives of those stars, tilting their paths over centuries and pulling their shapes tighter as if drawing constellations toward a gravitational focal point. It's worth holding both images in your mind at once, the violence of collapse and the serenity of order. A stellar progenitor might die in a spectacular supernova and leave behind a black hole. Meanwhile, At the center of a galaxy, a supermassive hole grows over epochs, orchestrating the motion of billions of stars. Both processes are extremes, but they produce the same kind of calm geometry, a region where possibilities funnel toward a single fate. This duality, born from catastrophe, operating with quiet, is what gives black holes their paradoxical allure. Think of it like stories you know. Life has its endings that feel definitive but actually change everything around them. A black hole's creation is an ending for a star, but it becomes the start of new dynamics. Jets that seed galaxies with chemicals, disks that light up and momentarily outshine entire galaxies, gravitational whispers that reach us as ripples in space-time. When a black hole tidies space, it is also shaping the story of the galaxy that hosts it. And finally, there's the human scale of wonder. When the EHT image came back, people around the world saw not just science, but a visual symbol of an idea grown into reality. For those who study black holes daily, it was a checkmark on predictions. For many others, it was a moment of shared awe that something so strange, so counterintuitive, can be rendered into a photograph by ingenuity and patience. If you ever feel small looking up at the night sky, consider that you share a cosmos with structures that, while immense and extreme, behave with a kind of tidy inevitability. They collect, they convert, they quiet. And over incomprehensibly long timescales, even they surrender their heat and vanish. In that quiet, there is a strange comfort. The universe is a place where endings are also transformations, where the harshness of a whole is softened by the calm logic of gravity and time. When two incredibly dense objects, black holes or neutron stars, dance together and finally collide, they don't just tug on the matter around them, they fling out ripples in space-time itself. Picture dropping a pebble into a still pond at midnight. The surface stays mostly calm, but concentric rings roll outward, carrying the memory of that one sudden event. Gravitational waves are those rings, traveling at the speed of light and carrying information about the splash that made them. The strange part is that by the time they reach us, the ripples are unimaginably tiny. They stretch and squeeze distances by amounts far smaller than an atomic nucleus. Yet with the right tools, we can detect them. On Earth, we build those tools as long, nearly empty tunnels with lasers fighting with mirrors. Two perpendicular arms, kilometers long, form an interferometer. A laser beam splits and races down both arms, bounces off mirrors, and returns to recombine. If space-time between the mirrors stretches in one direction and squeezes in the other, the returning light waves slip out of step and the pattern of light changes. That change is the whisper of a passing gravitational wave. To give you a sense of scale, LIGO's arms are 4 kilometers long, and the shifts it detects are around 1 part in 10^21. So the mirrors move by distances on the order of 10 to 18 meters, a fraction of the width of a proton. It's like measuring the difference between 2 points separated by the length of Los Angeles to an accuracy smaller than the size of a single grape seed. Those tiny changes show up as a familiar audio-like pattern when converted to sound. Early on in the inspiral of two compact objects, the signal is low and slow. Then it rises in both pitch and volume, a chirp as they race closer and orbit faster, culminating in a final crash and a deep, ringing tail called the ring down. That chirp is more than a pretty sound. Its frequency, sweep, and amplitude tell us the masses, how fast they're spinning, the distance to the source, and even the last few milliseconds of the object's lives just before horizons touch. It's as if you heard the last few heartbeats of two celestial giants and could deduce their size and condition from the rhythm. The first direct detection of such a chirp in 2015 felt like a miracle and a promise at once. Two black holes, each about 30 times the mass of the Sun, spiraled into one another roughly 1 billion light-years away. The signal lasted only a fraction of a second in the audible band of the detectors, but that tiny blip confirmed a prediction Albert Einstein had made a century earlier and opened an entirely new way to observe the universe. Before that moment, astronomy was almost entirely visual. Photons across the spectrum told the story. Gravitational waves gave us a new sense. With them, we don't see, we feel, we listen. Listening, however, is not just letting the detector record everything and hoping something stands out. The signals are faint and buried beneath a lot of noise, seismic tremors, tiny thermal vibrations in materials, quantum fluctuations of light, all of it. Scientists build elaborate isolation systems, suspending mirrors like pendulums to filter ground motion, operating in ultra-high vacuum so no air disturbs the beam, and using quantum tricks like squeezed light to reduce measurement noise. On the data side, we match the incoming blips against enormous banks of predicted waveforms. This matched filtering is like sliding a library of known songs across a static-filled recording until you find the one that lines up, revealing the best fit parameters of the source. The result is astonishingly precise, parameters with uncertainties small enough to test fundamental physics. What do we learn from a single chirp? Start with mass and spin. The way frequency evolves tells you the combined mass and how it's distributed. Subtle modulations reveal whether the objects were spinning and if their spins were aligned or tilted. The amplitude gives a measure of distance, though distance and the orientation of the binary are somewhat degenerate. If the orbit faces us head-on, the signal is stronger than if we see it edge-on. The final ring-down frequencies are the voice of the newborn object, usually a black hole, and they tell you about the mass and spin of that remnant. In some cases, especially with merging neutron stars, the in-spiral carries signatures of the internal structure, allowing us to probe how matter behaves at densities far beyond anything in terrestrial labs. That last point is where things became particularly human. In 2017, gravitational waves from two neutron stars merging, and the near simultaneous flash of gamma rays, and minutes to hours later, optical and infrared light, produced the first true multi-messenger astronomical event. Detected first as a faint chirp, and then seen as a fast fading glow called a kilonova. This collision gave us a complete narrative. The gravitational wave signal revealed the masses in dance. The gamma rays linked the event to short gamma ray bursts. The optical and infrared light showed heavy elements being forged in the explosion's aftermath. It was as if you heard a distant thunderclap and then watched the lightning. Beyond storytelling, that event let cosmologists measure the expansion rate of the universe by comparing the gravitational wave distance to the redshift measured from the host galaxy. A completely independent way to estimate the Hubble constant. It also confirmed that some of the universe's gold, platinum, and other heavy elements come from these violent mergers, making us feel connected to the cosmic production line of elements we hold dear. Gravitational wave astronomy also tests gravity itself in ways photons cannot. The waves travel at light speed to within astonishing precision. Comparing arrival times of gravitational waves and gamma rays from that neutron star in spiral showed they matched to within parts in 10^15. That rules out many alternative theories that predict different propagation speeds. The waveforms probe the strong field, highly dynamical regime of general relativity. The arena Einstein's equations describe, but which was previously impossible to observe. So far, the notes we hear match GR's score. The polarization, the energy loss rate, the final ring-down frequencies all line up with predictions. Yet every new chirp is a chance to strain the theory, to look for deviations that might whisper of new physics. The analogy of the midnight lake keeps proving useful. Most nights the surface is calm and silent. Then an unseen creature may break the surface, and long after the event, the ripples reach your shore. You never witnessed the leap, but the pattern on the water is proof enough. Gravitational waves give us the same kind of evidence, a causal imprint that tells a complete story without a single photon being exchanged. Black hole mergers, in particular, are largely dark in electromagnetic light. Without gravitational waves, we would have no idea they happened at all. Now, with a global network of detectors, LIGO's 2 observatories in the US, Virgo in Italy, Kagra in Japan, and more coming online, we can not only hear these events, but start to locate them on the sky, triangulating like sailors using multiple beacons. The more detectors listening, the better we localize, the faster telescopes can follow up, the richer the multi-messenger harvest. And the listening is only beginning. Detector upgrades push sensitivity deeper, widening the volume of space we can survey and increasing the rate at which we hear mergers. Future detectors, both on Earth and in space, promise to open new frequency bands. Space-based observatories will listen to slower, longer period waves from supermassive black hole binaries and pairs of compact objects in wide orbits, while ground-based facilities focus on the final furious moments. Scientists also search for a stochastic background, the faint, persistent hiss from countless unresolved sources or even primordial processes from the universe's infancy. Imagine standing beside that same lake and hearing, beneath every splash, a distant, continuous murmur that records the many small disturbances of a crowded ecosystem. That's what the gravitational wave background would be like, a cosmic chorus of countless sources. All of this is deeply human. We are rewiring our senses and extending them out to the cosmos. For most of human history, our tools for exploring the heavens were limited to what our eyes could see. Then we learned to extend vision with telescopes, to color it across wavelengths, to smell it with particle detectors, and taste it with neutrinos. Now we have ears attuned to the fabric of space-time itself. When you think about it, each detection is intimate. It's a recorded heartbeat from a system you'll never visit, a clue about the life cycle of stars, and a direct messenger from regions where gravity is at its fiercest. There's a humility in that. The universe can produce events far beyond our everyday comprehension, and yet, with patient engineering and curiosity, we can listen and learn. So next time you look up on a clear night, imagine lying by that midnight lake, Imagine tensioners tuning lasers instead of leaves rustling, vacuum pumps humming where frogs might croak, and scientists listening not with ears, but with interferometers. Somewhere out there, massive objects are waltzing and collapsing, and their steps send ripples that reach us as a faint chirp. It's a strange kind of intimacy. We never see the partners in that dance, but their music reaches across cosmic distances and speaks to us. We decode their story, and in doing so, we add another sense to our ancient gaze at the stars. You've seen stars as points of light, as pinpricks and smudges, as steady friends and flashing neighbors. But the picture is deeper. Stars are not silent, solid marbles floating in space. They're boiling, breathing spheres with beating hearts. And those hearts sing. Inside a star, gas is compressed and heated, and pressure waves travel through that seething interior, just like sound through air. Those waves are enormous and slow compared with anything we know on Earth. Some take minutes to bounce across the star. Others take days or months. We can't put an ear to a star. The notes are far too low for our hearing. But we can listen in other ways. Tiny changes in brightness, tiny shifts in the star's surface as gas moves back and forth. Let us read those notes like a score. This is the world of helioseismology and astroseismology. Helioseismology is the study of the sun's oscillations. Astroseismology is the same thing applied to other stars. The names sound technical and quiet, but the work is boisterous in its implications. By reading a star's vibrations, astronomers can map the unseen interior, measure rotation rates, track flows, and even weigh the core. It's like hearing the engine of a car while standing outside it and telling whether the pistons are worn, what kind of fuel it needs, and how many cylinders it has. How do we see those vibrations? Two main signatures. First, a star's surface brightens and dims as acoustic waves compress and rarefy the gas. Space telescopes like Kepler and TESS have given us measurements of brightness so precise that variations of a few parts per million are detectable. Second, parts of the star's surface move toward or away from us during an oscillation, producing Doppler shifts in spectral lines, a tiny blue shift, then a red shift. Combined, these signals are a diagnostic toolkit. Some stars beat with visibly obvious rhythms. Pulsating variable stars, Cepheids, RR Lyrae, Mira variables. Delta Scuti stars expand and contract in cycles, like lungs breathing. Those cycles are not random. For certain classes, the period of pulsation is tied directly to the star's intrinsic brightness. The longer the period, the brighter the star. That relation, first discovered by Henrietta Leavitt in the early 20th century for Cepheid variables, is one of astronomy's most powerful tools. It converts a measured tempo into an absolute luminosity. Compare that luminosity to how bright the star appears from Earth, and you have distance. That's how we began to ladder our way across the galaxy and beyond, and how Edwin Hubble used Cepheids to show that the spiral nebulae were entire galaxies outside our own. Think of a Cepheid as a giant metronome in the sky. Once you know its beat, you know its true voice. In regions where individual Cepheids are hard to find, other pulsating stars like RR Lyrae do the job inside globular clusters and close galactic neighborhoods. Put enough of these clocks together, and astronomers can map the architecture of the Milky Way and the distances to nearby galaxies. But the Sun, our nearest star, has its own orchestra. The Sun rings with countless overlapping modes: pressure waves, P modes, gravity waves, G modes, that probe deeper, and mixed modes that carry information across regions. The most famous are the 5-minute oscillations, packets of sound trapped in the Sun's outer layers. They bounce off the surface and refract back inward. Some modes circle the Sun's interior many times. By measuring the frequencies and shapes of these oscillations, helioseismologists have mapped the Sun's internal rotation, discovered that the outer convective zone spins at different rates with latitude, and identified a shear layer, the tachocline, that plays a key role in the solar dynamo and magnetic cycle. It's helpful to imagine standing in a cave and clapping hands. The echoes carry the cave's geometry, its hollows and ridges. Helioseismology is like listening to those echoes, but on a scale so huge, the cave is a star, and the echoes are slow, patient waves. From those echoes, we can see flows that would be invisible otherwise. Meridional circulations transporting heat and magnetic fields, subsurface jets that shepherd sunspots, and changes in the interior as the solar cycle waxes and wanes. Astroseismology extends that same logic to stars of different sizes, ages, and compositions. With Kepler's long, steady stare, we suddenly had light curves for tens of thousands of stars, sampled almost continuously. Instead of a few rare specimens, we now hear stellar music everywhere. Giant red stars sing long, low notes as their extended envelopes move. Sun-like stars murmur with many short modes. Some stars, especially those nearing the ends of their lives, produce characteristic oscillation patterns that let us weigh their cores and estimate ages to precision far better than traditional methods allowed. One of the most poetic stories comes from white dwarfs, the compact, cooling embers left behind when sun-like stars die. These small objects, about Earth-sized but as massive as the Sun, sometimes shiver. Certain white dwarfs pulsate with periods of hundreds to thousands of seconds. Those oscillations are not merely curiosities, they act as seismographs of extreme physics. In a white dwarf, the interior density becomes so high that the ions, carbon and oxygen in most cases, undergo phase changes and begin to form a crystalline lattice. Astroseismology reads the way pulsation modes change as a star cools and crystallizes. In effect, we can watch solids form out of a stellar fluid in real time. That's an astonishing claim. By listening to the tremors of an ancient star, we can infer the microscopic structure inside it. Beyond composition and crystallization, stellar vibrations reveal internal rotation gradients, core sizes, and mixing processes that dictate how stars live and die. Mixed modes in red giants, oscillations that behave like P modes in the envelope and G modes in the core, have let astronomers measure rotation rates of stellar cores versus envelopes, proving that cores spin faster than their outer layers. Those measurements inform models of angular momentum transport, with implications from supernova progenitors to how compact remnants form. All of this has practical consequences. Accurate stellar ages change our understanding of galactic history. Precise distances anchor the cosmic distance ladder. Better models of stellar interiors refine predictions of stellar yields, the chemical feedback that enriches future generations of stars and planets. The music of stars is not just a metaphor, it's physics translated into rhythm. And there's a human rhythm to it too. When you consider that stars keep time across millions and billions of years, their steadiness can feel quietly consoling. Our own hearts beat, and in a noisy world, it's easy to feel that pulse wobble. The stars demonstrate a different model of timing: patient, reliable, indifferent to human drama, but intimate in its constancy. If your chest feels tight or your thoughts race, imagine sinking to that slow, stellar breathing, long, even cycles like giants pacing through their lives, or the taut metronome of a cepheid that never misses its measure. You can turn that image into a small exercise. Breathe in for a count of 4, hold for 2, breathe out for 6, repeat. Picture a red giant expanding and contracting on a time scale far longer than ours. Imagine your in-breath matching its gentle swell and your out-breath echoing its collapse. Even if a star's oscillation is far slower than any human breath, borrowing its steadiness can be a useful metaphor, a way to reconnect with a broader rhythm that has nothing to prove and everything to sustain. There's also a humility in listening to stellar songs. We can measure a methodical beat and infer a history older than civilization. We can detect quantum-scale crystallization inside an object that could fit inside the Earth. The cosmos offers not just spectacular images, but a layered soundscape. Most of it sits below the range of hearing, but in its silence, it speaks volumes. Before we move on, one last human connection. Musicians and data scientists sometimes literally turn stellar oscillations into audible sound by compressing frequencies upward, a process called sonification. The results are haunting. The sun's 5-minute oscillations become a soft percussion. A red giant's long notes turn into low, sustained tones. Listening to those sonified tracks can be a visceral reminder that the universe is full of patterns and that our senses can be augmented to sense them. Whether you prefer to read a plot or listen to a converted oscillation, the point is the same. We are learning to hear the hidden life of stars. So when you watch the night sky next, try imagining not just points of light, but patient, rhythmic hearts. Stars pulse and sing. They ring like bells whose material is plasma and light. And if the small rhythms of your day feel jagged, borrow the steadiness of a star for a moment. Let that cosmic metronome remind you that some measures are slow and inevitable, and that in the long run, steady timing has a way of putting everything back in order. But not every world keeps a sun. Some planets are born with a star and later get unceremoniously kicked out by a gravitational shove, a close pass with a sibling planet, a visit from a passing star, or the chaotic shuffle of a young system where giant bodies rearrange the furniture. Others may have formed alone, collapsing quietly in a dark cloud the way a star might, only on a smaller scale. Either way, the result is the same: a planet with no schedule, no dawn, no sunset, a globe that wanders the galaxy on its own. Imagine standing on one of those places. There's no morning light to pull you out of sleep, no golden hour to make the rocks glow. The sky is a deep, uninterrupted black, punctuated by the distant, indifferent spark of stars. Any warmth a rogue world carries comes from within. Leftover heat from formation, slow radioactive decay in a rocky core, or residual contraction in a gassy giant. Without a nearby star, that heat is precious and finite, seeping through an atmosphere or insulating layers to make a narrow pocket of livable conditions, if conditions at all. When astronomers talk about rogue planets, they talk about islands in the dark. Some are rocky like Earth, some are bloated gas giants, the wandering cousins of Jupiter and Saturn. Others are in that gray area between planets and brown dwarfs, too small to sustain hydrogen fusion, but still large enough to glow faintly in the infrared. We've actually found a few of these free floaters. Objects like PSO J318.522, discovered drifting near the young Beta Pictoris moving group, don't orbit any star. They shine with their own heat, revealing themselves to surveys that scan the sky in infrared light. Detecting a planet with no star is like noticing a single ember in a cold night. Difficult, subtle, and often accidental. There are two main tricks astronomers use. The first is gravitational microlensing, a kind of cosmic coincidence. When a massive object passes directly between us and a background star, its gravity bends and magnifies the star's light, producing a brief, distinctive brightening. If that foreground object is a planet, the magnification can be very short, maybe hours or days, but telltale. Microlensing surveys like Ogle and Moe have found events that hint at free-floating planets, and because the technique doesn't rely on the foreground object emitting light, it can reveal truly dark wanderers. The other approach is infrared astronomy. Rogue giants, especially younger ones, are still warm enough to glow in mid and far infrared. Telescopes like WISE, Spitzer, and now JWST can pick up that faint thermal signature. A dot of heat in a sea of cold is a clue that something substantial sits out there emitting its own warmth. Sometimes follow-up observations confirm that the object isn't tied to any nearby star. It just sits on its own, a drifting heat source against the black. How many of these are out there? Estimates vary, but some studies suggest there could be billions of rogue planets in the Milky Way, maybe even outnumbering the stars. Those numbers depend on assumptions about planet formation and early system dynamics. Young planetary systems can be chaotic. When massive planets form quickly, they can scatter one another, flinging smaller worlds into interstellar space. In crowded stellar nurseries, passing stars can disrupt nascent systems, sending planets on long journeys. If even a modest fraction of systems eject a planet or two during their youth, the tally across hundreds of billions of stars becomes enormous. It's easy to let the image settle into something lonely, a cosmic loneliness we project onto these objects. And yes, there's a kind of isolation in being a world without a sun. But there's also a different mood, not desperation, but a quiet, relentless continuity. No alternating of seasons, no hurried cycles of day and night. Just long, slow nights, broken only by the distant flicker of suns too far to warm anything. That absence can feel freeing. Think of a place with no clock, no pulling tides of light and dark, where temperatures shift only on geological timescales. For a planet, drifting becomes a state of being rather than a crisis. There are interesting implications for habitability and for what life might look like in such a place. A planet with a thick hydrogen atmosphere could trap heat extremely efficiently, creating surface conditions warmer than you might expect, despite the absence of stellar light. Deep oceans insulated by ice and warmed internally, a subsurface sea like the ones we imagine on icy moons, might persist for eons. These are theoretical, of course. We don't have evidence of life on rogue planets. But the physics allows for pockets of stability that, in principle, could be long-lived and chemically interesting. On a personal level, you can draw a metaphor from this. Feeling untethered or directionless is not always a sign that something is wrong. Sometimes, like a rogue planet, you're simply between anchors, carrying your own warmth, moving under forces you can't always see, and still whole. When your schedule disappears, or when the people around you change, the instinct is to panic, to chase a new center. But drifting is also an option. It lets you regroup, conserve energy, explore different parts of your orbit through life without the constant pull of a single dominating sun. That idea, that drifting can be natural, is strangely comforting. The cosmos contains countless examples of entities that are not bound to one pattern or one anchor. They don't necessarily cease to be valuable or interesting because they aren't part of a system we recognize. Instead, they offer a different kind of existence, slower, less choreographed, potentially lonelier, but also less pressured. There's peace in that. Visualize one of these worlds for a moment. It might be a black, basaltic rock with a thin, misty atmosphere and an aurora occasionally sputtering as cosmic rays strike magnetic fields. Or imagine a swollen gas giant, ribbed with storms, glowing a dull red in the infrared as heat leaks from its interior. The surface, if there is a solid surface, would have no painted skies of sunrise and sunset. You'd only see stars, their positions steady over hours, with a sky so dark you could read the faint structure of the Milky Way with the naked eye. If lightning occurs, it would be local, dramatic, and unendingly stark against an absolute dark. Even on a small scale, these worlds can be dramatic stage sets. When a rogue planet drifts near a star, not close enough to capture it permanently, but close enough for a brief encounter, tidal forces can create short bursts of activity, an increase in volcanic eruptions, the heating of oceans, a temporary, if rare, thawing of surfaces. Those close encounters are short-lived on geological timescales, but they remind us that drift is not necessarily static. A wandering planet can be nudged, torqued, and at times briefly lit by another star's glow before it continues on. Astronomically, every detection of a rogue planet is a small triumph. Microlensing detections are fleeting, so they require constant monitoring. Infrared detections require sensitivity and patience. JWST, with its incredible infrared sensitivity, is poised to peel back more of this shadowy population. Future surveys, both ground and space-based, will refine the census. Will we find more Earth mass rogues than massive giants? How many were formed in place versus how many were cast out? Those questions will help fill in the story of how common planetary ejections are and what that means for the architecture of planetary systems. For viewers watching at home, the science is fascinating, but the emotional takeaways are maybe even more useful. When you're drifting, when you feel like you've been unplugged from a life or a plan, it's not necessarily an emergency. It might be a phase. Like a planet with internal heat, you carry resources that keep you going. Skills, memories, a tolerance for solitude, a capacity for curiosity. You can stay warm inside, at least for a while. And drifting can be a form of exploration. A rogue planet left to wander will eventually pass through different neighborhoods of the galaxy. It will sample new radiation environments, encounter different clouds of interstellar gas, and potentially gain or lose satellites in the process. There's a kind of slow adventure to that. So when the inner calendar collapses and the regular rhythms stop, try to think not only of the absence, but also of what the absence allows. You can move in ways you couldn't when you were bound to a star. You can discover, collect, and reflect. You can reset. The galaxy, after all, is not only made of bright, comfortably categorized things arranged neatly around centers. It's also full of strays, wanderers, outliers that carry their own light. To close this section, picture the steady flicker of distant suns from the vantage of a world with no sun. The view is the same for all of us sometimes. Small pinpricks of possibility in a vast dark. But remember the warmth that can come from within. Rogue worlds aren't only cold, they can be quietly hot, moving, resilient. If you feel untethered, let that image be permission to keep warm by what you already have, to let drift be a phase rather than a failure, and to trust that being untethered can still mean being whole. Picture the skeleton left behind when a giant star has used up its fuel and can't hold itself up anymore. The outer layers blow away in a supernova, brilliant enough to outshine a whole galaxy for a moment, and the core, whatever mass is left, gets squeezed down until it can't get any smaller without breaking the rules of quantum mechanics. What you end up with is a sphere maybe 20 kilometers across, about the size of a small city. That tiny globe contains more mass than our sun, packed so tightly that atoms as we know them don't survive. Electrons are forced into protons, making neutrons the dominant building block. You get a city-sized ball of essentially pure neutron matter. It's a hard thing to wrap your head around because the numbers refuse to behave like the world you touch every day. A teaspoon of that stuff, a literal teaspoon, would weigh on the order of billions of tons. Say those words out loud next time you're stirring your coffee. A spoonful heavier than some mountains. That's not a flourish. It's a real, calculable fact. The density inside a neutron star is comparable to that of an atomic nucleus. The distance between particles is shrunk to the point where the strong nuclear force starts to matter on a macroscopic scale. It's a realm where common metaphors for heavy and small swap places. But mass and density are only part of the story. Neutron stars are restless and theatrical. Some of them spin like cosmic fidget spinners, not once a minute or once a second, but hundreds of times each second. When a massive star collapses, conservation of angular momentum makes the core spin faster and faster the smaller it gets, just like an ice skater pulling in their arms. When that spin is channeled along a magnetic axis that doesn't line up with the rotational axis, the star emits beams of radiation that sweep through space like the beam of a lighthouse. If one of those beams crosses Earth, we see a pulse, hence the name pulsar. In 1967, Jocelyn Bell Burnell noticed precisely timed radio pulses that led to the discovery of these objects. At first, they were jokingly called little green men, because the pattern was so regular it seemed almost artificial. Those beams act like clocks. Millisecond pulsars, neutron stars that have been spun up by stealing material from a companion star, can rotate hundreds of times each second, and their pulses arrive with astonishing regularity. Over years, the timing of a well-behaved millisecond pulsar can rival the stability of the best atomic clocks. That's not to say they're perfect. Pulsars can have hiccups, called glitches, when their rotation suddenly jumps a little faster because the superfluid interior redistributes angular momentum. But despite those idiosyncrasies, pulsars allow astronomers to measure tiny effects in gravity, to test general relativity, and even to try to detect gravitational waves by watching the slow, coordinated tugging on an array of pulsars spread across the sky. Then there are the show-offs, magnetars. If a pulsar is a precise lighthouse, a magnetar is a magnetic tantrum. Their magnetic fields are stupendously strong, a few thousand trillion times stronger than Earth's field, enough to twist atoms into long, thin rods and to reshape the surface of the star itself. When a magnetar's magnetic field suddenly rearranges, it can release an enormous amount of energy in a pulse of X-rays and gamma rays. One giant flare observed in 2004 from SGR 1806-20 was so powerful it affected Earth's upper atmosphere, despite being tens of thousands of light years away. That's the kind of violence that makes headlines. A tiny object, barely bigger than a city, unleashing as much energy in a fraction of a second as our sun emits in hundreds of thousands of years. Inside these stars, weird states of matter rule. The neutrons themselves can form a superfluid, a fluid with zero viscosity, and the leftover protons can become superconducting. The interior behaves like something out of condensed matter physics on steroids. Those properties explain some puzzling behaviors we observe, like the aforementioned glitches. If the superfluid interior is loosely coupled to the crust, angular momentum can be transferred suddenly, causing the observed spin-up. Starquakes, when the crust rearranges itself after being twisted by magnetic stresses, can shake the star and produce bursts of high-energy radiation. The word quake is apt because, in a way, these are tectonic events on something with a gravity field 1 billion times stronger than Earth's. But for all the extremes, the crushing density, the frenetic spin, the magnetic tantrums, neutron stars also have a kind of quiet reliability. Think of a metronome on an instrument. It keeps time, steady, and patient. Pulsars do that on cosmic scales. Scientists use them as references, as tools, because their pulse trains are so predictable. A system of pulsars can be used like a galaxy-sized detector for long wavelength gravitational waves. Tiny deviations in timing across that network could signal the passing of ripples in space-time produced by supermassive black hole binaries. That sensitivity to subtle change makes neutron stars not just objects of spectacle, but instruments in laboratories. Bring it down to something human for a moment. You're holding your coffee, seeing the teaspoon comparison in your head. The neutron star is both minuscule and monumental. Small in size, enormous in meaning and effect. It's a reminder that scale is tricky. Small doesn't always mean light or simple. Quiet can contain overwhelming force. A metronome can also be a sledgehammer. A single steady beat can be a measure for the rest of the universe. Imagine your thoughts when they feel scattered. Dozens of tabs open in your head, pinging like notifications. Now imagine a neutron star's calm momentum, a tiny city spinning in the dark, arms flung wide, keeping time for itself and anyone watching. Its pulse is a steady, patient thing that persists through explosions and earthquakes and magnetic storms. There's something soothing about that persistence. It says, even in the most extreme places, order can emerge. Even under impossible pressure, systems can settle into a reliable rhythm. And yet, these stars also teach us about sudden change. Just when the pace seems predictable, a magnetar flare or a pulsar glitch reminds us that stability and catastrophe are not opposites, but neighbors. The same object that ticks like a clock can hiccup or erupt, and when it does, the consequences reach across light years. That duality is familiar to anyone who's ever been calm, and then suddenly not. The quiet surface can mask immense potential for upheaval. It's not just astrophysics, it's human too. There's another human thread here. We use neutron stars as tools to answer questions about ourselves and the universe. Pulsar timing lets us measure distances, probe gravitational theories, and even think about the possibility of sending time signals across interstellar distances. The precision of some pulsars is so great that they've been proposed as a navigation aid for future spacecraft, a galactic GPS, if you will. The irony is beautiful. An object born in death, the leftover core of a star that exploded, can help guide journeys and test the laws of physics that let us understand everything from atoms to galaxies. So when you next feel swallowed by scale, when a single person's influence feels small, or when a problem seems insurmountable, remember the neutron star. In a teaspoon, an almost unimaginable weight. In a pulse, a clock steadier than many devices we build. In a flare, energy that can shake the space between stars. The universe stacks extremes in the same place, tiny and immense, quiet and violent, precise and capricious. That contradiction is not a failure of explanation, but a feature of the cosmos. It's the kind of reminder that can make patience feel natural again. Small things can hold tremendous depth. Weight and quiet can share the same place. As the scene closes in your mind, picture that city-sized sphere spinning in the dark. Hear its beat, steady, faint, unwavering. Let that steady turning be a kind of permission slip, permission to be small and complex at once. The universe keeps its own time, with both delicacy and force, and somewhere in that rhythm there's room for us to measure, to marvel, and occasionally to be moved. Out here, our solar system drifts through a wide, quiet room in the galaxy, the local bubble. Picture a soft, sunlit living room after a storm, furniture upright, trees quietly shedding the last leaves, a sense that something wild happened not long ago, but has long since settled into calm. That's the local bubble in cosmic terms, a vast cavity of thinner, hotter gas carved into the interstellar medium by ancient, violent events so long ago, no human stood to witness them. They left behind more than ashes. They left a neighborhood. Start with the scale. The local bubble stretches for hundreds of light years in most directions. That's not a tidy sphere you could put on a drawing. It's a complex, lumpy cavity with ragged edges, a region where the density of gas is dramatically lower than the average between the stars. Where a typical patch of interstellar space might contain roughly 1 atom per cubic centimeter or more, inside this bubble, the gas is far more rarefied and, paradoxically, far hotter. The interior is filled with a tenuous million-degree plasma that emits faint X-rays, a whisper of heat from explosions many millions of years old. Around the edges of that cavity, where the bubble runs into denser clouds, the story changes. Dust and gas pile up, cool, and begin to craft the raw materials for new generations of stars. The edges are alive. How did it form? The best explanation is one that sounds dramatic, but is also wonderfully simple: supernovae. Multiple massive stars in our stellar neighborhood lived fast and died young, each ending in a brilliant explosion that blasted away surrounding gas and heated what remained. Those explosions don't happen in isolation. In a clustered stellar environment, the shockwaves can overlap and carve out a large interconnected void. Over tens of millions of years, that void expanded and cooled, leaving the kind of low-density cavity we now call the local bubble. Think of a forest of tall trees struck by lightning in several places. The fires merge into clearings, and the pattern of burned and unburned ground becomes the new terrain. The local bubble is the galactic equivalent. It's important to remember that this is not something you could notice standing on Earth. You cannot feel a bubble passing or see a draft the way you would with weather here on the planet. But its influence is more subtle and no less real. The local bubble is background, the quiet room in the larger house of the Milky Way. Because it is more empty than the surrounding medium, it softens certain types of cosmic weather. For example, light from distant stars travels through less dust and gas on average when it reaches us, so starlight is less reddened and less dimmed than it would be if we were embedded in denser clouds. That means astronomers looking outward are, in a sense, peering through a window that has been cleaned for them. Some colors come through more clearly. Some faint structures are easier to spot. The bubble affects our measurements and our sense of where things lie in three-dimensional space. The bubble also shapes how particles and magnetic fields behave near us. The heliosphere, the protective bubble formed by the sun's solar wind, expands and contracts depending on the pressure of the surrounding interstellar medium. In a low-density environment, the heliosphere can be more extended. In a denser medium, it would be compressed. So the air of this galactic living room changes the shape of the sun's own little bubble, and therefore the steady stream of energetic particles that reach Earth's neighborhood. Cosmic rays, magnetic fluctuations, the interplay of charged particles with dust. All of these are filtered and modulated by the cavity we occupy. It's a form of cosmic weather that rarely makes the headlines, but it quietly conditions the space environment the entire solar system swims through. Astronomers didn't stumble on the local bubble by chance. They mapped it by combining many kinds of observations: how stars' light is reddened by dust, measurements of neutral hydrogen via radio observations, the absorption lines of different elements in stellar spectra, and the faint glow of soft X-rays from the million-degree gas inside. Put together, these data sketch a cavity: tenuous interior, brighter shells around the edges, pockets of denser material where new stars are forming. In some directions, the shell is nearby. In others, it reaches farther. Where the shell curves and collides with neighboring clouds, the gas compresses, cools, and forms the seeds of star birth. So the same family of explosions that cleared the interior also helped set the stage for new stellar nurseries at the bubble's rim. This is one of those poetic ironies of the universe. Destruction and creation are intimate partners. The supernovae that birthed the local bubble were cataclysmic events that ended lives of massive stars in a violent instant. But their shockwaves swept up gas and dust, piled it into dense ridges, and in those ridges, the next generation of stars could form. If you like neighborhood metaphors, imagine a city block knocked down by a storm. In the rubble, some seeds find a soil niche and take root. Saplings grow in the cracks, and decades later, there's life where wreckage once lay. On cosmic timescales, tumult eventually softens into calm, and that calm can be the very condition that makes new things possible. Make it personal for a moment. If you look up at the night sky and feel small or lonely, consider this. The space around you, the invisible medium this planet and your life sit inside, was shaped by explosions long before our species existed. The local bubble is a kind of inherited calm. It's like living in a town where long ago fires cleared the brush and left a park. You walk that park without needing to tend the clearing yourself, yet your ability to see across it, to breathe on its open paths, exists because of what happened before. There's a comforting humility in that. The stars we admire tonight formed on ridges of gas lifted and compressed by processes that had nothing to do with us. Yet those processes helped shape the gentle conditions we now experience. And that gentleness matters for science. When astronomers try to measure the cosmic microwave background, map the faint halos around galaxies, or trace the origins of interstellar dust grains that eventually find their way into meteorites, they must account for the local conditions. The local bubble filters incoming radiation and particles in subtle ways. When a mission like IBEX or Voyager crosses the outer reaches of the heliosphere, the readings it returns are influenced by the density, temperature, and magnetic field of the medium outside. When we calibrate telescopes and interpret spectra, we need to know whether the light we see has passed through dense clouds that would redden and absorb it, or whether it has traversed the nearly empty interior of a bubble. There are smaller structures inside the bubble too. Within this broader cavity, there are islands of slightly denser gas. Like the local interstellar cloud, sometimes called the local fluff, that the sun is currently wandering through. These local patches are still extremely tenuous by earthly standards, but they have subtle effects on interstellar material that reaches the heliosphere. The motion of the sun relative to these local clouds, the angle of the magnetic field, even temperature differences on a cosmic scale can nudge where and how particles interact with the edges of our solar system. It's a delicate choreography, and we are living right in the middle of it. Visually, if you could paint the neighborhood at different wavelengths, it would look like a textured, layered landscape. In optical light, the bubble's interior is mostly empty, few dust grains to scatter and redden starlight. In radio, you'd see the denser clouds at the boundaries traced out by neutral hydrogen emission. In X-rays, the hot interior would glow faintly, a diffuse wash across the sky. And in ultraviolet absorption lines, the signatures of the intervening gas would reveal the velocity and composition of what lies between the stars. Each observational tool gives part of the picture. Together, they narrate the bubble's birth, evolution, and relationship to surrounding structures. Now consider what this means for our perspective as observers and storytellers of the cosmos. We like to think of the universe as an immutable backdrop, a star field we can step back from and view objectively. But the local bubble is a reminder that our vantage point is itself a product of the galaxy's history. The light that reaches our telescopes is filtered. The particles that reach our detectors are moderated. And even the future of our cosmic environment depends on slow motions and long-lived structures that began before humans existed. It invites a kind of historical humility. The night sky we inherit is shaped by events whose echoes we can still measure, but not events we participated in. And there's an emotional thread in that too. It can be comforting to remember that our neighborhood was prepared by events we never saw. The hush after a storm can feel protective. You can stand in a quiet clearing and feel the absence of chaos as a blessing. In the broader sense, the local bubble offers that same hush, a region of relative calm in a dynamic, sometimes violent galaxy. That calm gives space for life-supporting planets to orbit without being constantly battered by dense clouds, for star formation at the edges to be orderly rather than chaotic, and for astronomers to peer deeply into the cosmos with clearer eyes. So when you next look up and feel the pinch of time, the sense that everything changes, that the cosmos is far older than us, that we are small, remember this detail. The very place we sit in the galaxy was hewn by storms that cooled into quiet. We are inside a cavity, a careful clearing made by supernovae, whose light faded long before primates left the trees. Their fury became a gentle neighborhood. That line, that idea, is oddly consoling. It suggests that violence, given vast stretches of time, can yield shelter and order. Turmoil calms, chaos organizes, and what we call home, both in the immediate sense of Earth and in the larger sense of our solar system's surroundings, is a direct product of that slow transformation. Because we live inside that hush, many of the practical things about how starlight and particles reach us are affected. Astronomically, that means cleaner sightlines, a different balance of cosmic radiation, and a heliosphere shaped by low external pressure. Culturally, it means our myths and metaphors, storms giving way to clearings, ancient fires seeding new growth, resonate with the real physical history of our corner of the galaxy. The local bubble is both a physical reality and a poetic touchstone. Finally, it's worth remembering that the local bubble is not permanent. The galaxy is dynamic. Gas drifts, stars move, and in a few tens or hundreds of millions of years, our local environment will be different. We might drift into a denser cloud, or neighboring supernovae might create new cavities that reshape the neighborhood. For now, though, we are in this gentle cavity, a gift from distant, bygone explosions that now only whisper through the glow of their leftovers. It's a cosmic moment of quiet, and when you picture the night sky after that long, ancient tumult, it can be reassuring. Even the universe has storms that eventually become calm, and inside that calm we get to be observers, explorers, and residents all at once. So time isn't a metronome that ticks the same everywhere. It's flexible. It bends and stretches depending on where you are and how you move. That's not poetry. It's physics. Einstein told us that space and time are woven together, and that gravity and motion can change the rate at which clocks tick. Here's what that really means, and how it shows up in machines, in the cosmos, and in the small, quiet ways you feel it in your life. Imagine two identical clocks. Put one on a table in your living room and strap the other to a satellite whizzing around Earth. Leave them running for a few days and compare. They won't agree. The satellite clock will have drifted. Not by much, fractions of a millisecond, but enough that if we ignored it, the navigation apps in our pockets would misplace you by kilometers every day. The reason comes down to two effects Einstein predicted. First, motion. Special relativity says that if something is moving relative to you, its clock runs more slowly. The faster it moves, the more pronounced the slowdown. That's called time dilation. Satellites orbit quickly, so their onboard clocks lose a little time relative to clocks on the ground. Second, gravity. General relativity says that the stronger the gravitational field, the slower time passes. Put a clock closer to a massive object, and it ticks more slowly than one farther away. Since an orbiting satellite is farther from Earth's mass than you are on the surface, its clock ticks a bit faster because it experiences weaker gravity. On GPS satellites, the two effects compete, and the net result is that the satellite clocks tick faster than identical ground-based clocks by about 38 microseconds per day. That's tiny in absolute terms, but in GPS world tiny is catastrophic. Without correcting for those 38 microseconds, your phone would be telling you the wrong location by roughly 10 kilometers every single day. So engineers add relativistic corrections into the system's software and hardware. Atomic clocks plus Einstein's equations keep your directions accurate. The modern marvel that helps you find a coffee shop is literally built on the idea that time runs differently depending on where you are. We've tested this idea in lab experiments too. When physicists flew atomic clocks on planes, the moving clocks lagged behind identical clocks left on the ground, exactly as predicted. We've measured time running differently at different heights. Atomic clocks are now so precise that a change in elevation of just a few centimeters can produce a measurable time difference. Time's flexibility has graduated from theoretical oddity to everyday engineering requirement and laboratory reality. Now imagine that flexibility turned up to 11, close to extremely massive compact objects. Black holes, for instance. Time stretches dramatically. Around a black hole, space is crumpled so severely that if you hover close to the event horizon, your watch ticks at a snail's pace compared to someone far away. From the outside, watching someone fall in, their seconds become long, and their motions smear out in slow motion. The mathematics tells us that as you approach the event horizon, time dilation relative to a distant observer grows without bound. The idea that minutes near the horizon can equal years far away isn't a sci-fi exaggeration. It's the natural consequence of how gravity warps space-time. That's a striking image. A brief conversation, a single breath. A minute of hand-holding near a horizon could correspond to lifetimes for those left in a distant galaxy. It's not just the extreme newscast version of relativity. It's an invitation to rethink what now means. The person near the black hole experiences their moment normally. Their heart beats, their thoughts come and go at the same pace to them. It's only comparing between vantage points that time's rates diverge wildly. On the largest scales, time's behavior carries a different kind of memory, not of local gravity wells, but of the universe's own history. Cosmologists often talk about cosmic time, a clock that measures the age of the universe as experienced by observers moving with the cosmic expansion. That shared cosmic time records a story: how space stretched, how the energy density cooled, how particles settled into the structures that eventually formed galaxies, planets, and people. When the universe was young, it was hot and dense. Things happened quickly. As it expanded, it cooled. Processes slowed and turned into new ones. The rate of expansion at different epochs tells us when certain transitions happened, when protons and neutrons fused into light elements, when atoms formed and the universe went from opaque to transparent, when the first stars ignited. The cosmic microwave background is essentially the universe's baby photo, a snapshot of the time when the universe first became transparent and photons could travel freely. In that sense, the flow of time on cosmological scales is stamped with the memory of expansion and cooling. It's not that time itself changes its fundamental nature, but the rhythm of events, the tempo at which physical processes occur, is set by how the universe stretches. There's another, deeper imprint too: the arrow of time. The universe's initial conditions were very low in entropy, which allowed complexity, from atoms to life, to unfold. That low entropy beginning gives time its direction, from simpler, smoother early moments to the rich, disorder-increasing present. In that sense, time's flow is a story about history embedded in physical law. The universe's expansion offers the stage, and the cooling provides the cues. Time is how the play proceeds. All of this can feel abstract, but you can make it intimate. Picture a river. In the middle, the current runs swift. Along the banks, it's lazy and slow. Rocks force eddies and whirlpools. Wider, calmer pools invite you to float and rest. Time is like that river, faster through the channel where conditions push it along, gentler near the edges where gravity or motion have a slowing hand. You're not a fixed marker on the riverbank. You're in the water, bobbing and moving with it. Sometimes you drift with the current, sometimes you paddle, sometimes you anchor and let the pool wash your worries away. That image helps tie the physical to the personal. When you're running late, the minutes feel like they're sprinting past in the river's middle. When you're lying awake at night, staring at the ceiling, time seems to widen into a pool. Everything stretches, and breaths take on more room. There is no contradiction between an atomic clock's precise count and your felt experience. The wall clock will dutifully mark seconds, but your body marks moments. A pause in conversation, a laugh that lingers, a hand pressed to a loved one's. Those subjective durations are softer and kinder metrics of living. There's an elegant humility in that. Physics doesn't demand that your experience of time be reduced to a number. The equations tell us how proper time, the time experienced along a physicist's world line, behaves under different conditions. You have your own proper time. The beat, set by your metabolism, by your rhythm of attention, by the emotional weight of an hour. Science offers explanations and corrections when we compare clocks across space and velocity, and it gives us tools, GPS is one, that depend on those corrections. But it also leaves room for the human scales of waiting, savoring, worrying, and letting go. That space between precise clocks and felt moments is worth exploring every now and then. Try this. Late tonight, when the day has softened and devices dim, notice how time feels. count out 5 breaths and notice the space that opens. Your phone will mark 50 seconds. Your body may have traversed a small eternity of thought in that interval, or very little at all. Both are true. The world has layers of time, physics measuring with extreme fidelity, your interior life passing at a pace set by mood and attention, and the cosmos unfolding across billions of years. We use the language of clocks and equations to build technologies and to understand black holes and cosmic history, but we also live inside time's ebb and flow. If you've ever watched someone asleep and thought the world had slowed down, that's not a metaphor. That's your perception aligning with a different tempo. If you have ever stood under an enormous tree or at an ocean cliff and felt your heartbeat match the slow, patient scale of geological or tidal rhythms, you've tasted time on other scales entirely. That is part of the beauty. Physics explains the mechanisms that make these experiences possible without stealing their mystery. It's also comforting to remember that being slower sometimes is not a failing but an alignment. Near the banks of the river, the water is calmer. You can breathe, notice, and choose. When life's pressure feels like an accelerating current, it helps to notice that parts of time's flow are under your stewardship. You can change how you ride it. The cosmos imposes constraints, gravity's pull, the speed of light. But within those constraints, there's scope for meaning. A minute on a mountaintop can hold a lifetime's worth of reflection. An afternoon with a friend can collapse years of distance into intimacy. So the clocks on satellites get tuned, experiments confirm the bending of time, and astronomers read the universe's early clocks in the sky. Meanwhile, in your bedroom, your kitchen, and the places you pass through, time will continue to have those soft edges. Let the scientific picture inform you without erasing the personal one. Let the knowledge that time is flexible be an invitation to marvel at the precision that guides our technology, to be awed by the scale of black holes, and to honor the small, elastic moments that make life meaningful. As we move forward, keep that river in mind, a current shaped by gravity and motion, by cosmic expansion and local mood. Up ahead, we'll look at how information rides that river, how signals stretch and fade across space, how causality maps onto time's flexible geometry, and how the very idea of before and after is stitched into the fabric of the universe. But for now, breathe. Count your subtle moments. Let time's gentle variance be part of the landscape you move through, not just an equation on a page. Every so often, a distant galaxy, a nearer galaxy, and our small vantage point arrange themselves along one line. The foreground mass bends the background light into a near-perfect loop called an Einstein ring. Imagine looking at a tiny candle through the base of a glass bottle. The flame doesn't stretch or change shape. What changes is your path to it. Seen through that curved glass, the flame becomes a rim of light. The candle hasn't become circular. The route from the candle to your eye has. That's the heart of an Einstein ring. Not a true circle painted on the sky, but a circle in the paths that photons take. Space has become pliable around mass, and the light traces that pliability. Picture the scene for a moment. There's a massive galaxy between you and a faraway, fainter galaxy. If that foreground galaxy is very nearly centered on the line of sight, the light from the background galaxy arrives at your telescope from every direction around the lens, bent into a loop. If the alignment is perfect and the lens is nicely symmetric, you get a clean, striking ring, a halo of light that frames the lensing galaxy. If the alignment is a little off, you get arcs or two or more separated images instead. That single difference, a hair's breadth in cosmic scales, decides whether you behold a ring, a horseshoe, or something fragmented like a crystal chandelier of images. Why does this matter beyond the aesthetic? Because an Einstein ring is a measurement tool disguised as a jewel. The ring's radius, the angular size from the center of the lens to the ring, is set by the total mass inside that circle. That includes all the visible stars and gas and all the invisible stuff, the dark matter halo that otherwise refuses to show itself. In that way, the ring is a scale. The wider the loop, the heavier the lens. Astronomers call this scale the Einstein radius, and it's a clean, physical number we can extract from images. No assumptions about how bright the stars should be. No guesses about unseen ingredients. Just gravity bending light. There's an intimacy in that measurement. It's like walking up to a closed door and telling how heavy the house inside must be, only by watching how the doorknob swings a little when you press it. The ring tells us about mass in a way that light alone never can. You could measure the light from the lensing galaxy and lump together every star you see, but that would miss the dark scaffolding holding the whole thing together. Those unseen components betray themselves by how they bend light. Einstein rings, then, let us weigh galaxies without opening them up. But the rings offer more than a single number. They trace, in exquisite detail, the distribution of mass. A perfectly smooth lens creates a smooth circle, small clumps of mass, like dark matter satellites, ripple the ring, tiny brightness fluctuations or kinks that would not exist otherwise. Those ripples are like fingerprints of dark matter substructure. Observers who model the ring carefully can pick out the signature of a 10 million solar mass clump hiding in the halo, even if that clump has no stars to light it. In practice, lens modelers build a mathematical map of gravity that reproduces the ring's shape and brightness. Discrepancies between model and data point to the invisible lumps. Over time, collecting many rings lets astronomers reconstruct how dark matter clusters at small scales, a test of the fundamental nature of dark matter itself. There's another layer too. Rings amplify. The foreground galaxy acts as a natural telescope, concentrating the light from the background source. That magnification lets us study galaxies that would otherwise be too faint or too small to see in detail. It's as if nature provides a zoom lens at no charge. By analyzing the distorted, magnified image, astronomers can peer at star formation in the early universe on scales normally impossible to resolve. The ring is therefore both scale and microscope. All of this depends on geometry. The precise size of the Einstein radius depends not only on the lens's mass, but on the distances between observer, lens, and background source. Move the background galaxy further away, keeping the lens mass fixed, and the ring grows. That's why double Einstein rings are so prized. Sometimes, by coincidence, two background galaxies at different distances line up behind the same foreground lens. You then get two concentric rings with different radii. With those, astronomers can compare the amount of bending at two distance scales and extract cosmological information, constraints on the universe's expansion history, in ways that a single ring cannot provide. But why are rings so rare? Because the alignment requirements are strict. The foreground mass has to sit almost exactly along the line of sight to the background source. Galaxies are tiny targets on the celestial stage, so getting that geometry is a low probability event. Large sky surveys, like the Sloan Digital Sky Survey and later deeper imaging campaigns, were crucial. They gave us enough galaxies that the rare alignments could be found. And when a ring is discovered, it feels special, a cosmic coincidence captured on film. Seeing an Einstein ring is emotionally striking the first time. For professional astronomers, it's a rush, a clear, direct consequence of general relativity, bending light like a fingerprint, and accessible with current instruments. For the curious viewer, it's a reminder that the universe is hands-on with light, that the route matters almost as much as the origin. We recognize the foreground galaxy and the background one as separate things with separate histories and contents. The ring tells us that the space between them is active, curving, and revealing secrets. The technical work to extract those secrets is part detective story, part sculptor's craft. Observers gather high-resolution images across wavelengths, optical to infrared and sometimes radio, and match them with spectroscopy to pin down the redshifts, the distances of lens and source. Then modelers construct mass maps that could plausibly bend the source into the observed ring. Those maps aren't arbitrary. They are constrained by physics and by the galaxy's visible structure. The best models typically combine a smooth component that tracks the galaxy's stars and a more extended halo for dark matter. Residual mismatches between the model and image can suggest substructures, satellite galaxies, or even exotic possibilities like compact dark objects. An accessible way to think about that modeling is to imagine shining a flashlight through a piece of frosted glass onto a wall. The pattern on the wall tells you something about the glass's thickness and texture. By adjusting your guess for what the glass looks like until the simulated pattern matches the observed one, you learn about the glass. In gravitational lensing, the pattern is the ring. The glass is the mass distribution bending the light. That inversion from image back to mass is why rings are so valuable. Einstein rings also become laboratories for subtle physics. One example. If the background source is a quasar, a compact variable beacon, different parts of the ring correspond to light that took different paths and thus different travel times. Small differences in arrival times can be measured if the source varies in brightness, and those time delays can be combined with models to infer the absolute scale of the universe's expansion. This is the same principle behind measuring Hubble's constant with lensed quasars, although rings themselves are typically from extended galaxies rather than point-like quasars. Another subtlety is that gravitational lensing is achromatic. Gravity bends all wavelengths equally, but different wavelengths might originate in different physical regions of the source galaxy. So comparing how the ring looks in radio, infrared, and visible light can teach us about the distribution of stars, dust, and active regions in the background galaxy. Radio observations can reveal structure that optical images blur, while infrared can penetrate dust. The combination becomes a multi-wavelength portrait, reconstructed through the distorting glass of gravity. Some of the most exciting uses of rings come from carefully studying their imperfections. If a ring shows a tiny bend or a blotchy brightness change, it could be evidence of a dark matter clump of fraction, the mass of the Milky Way. Detecting these clumps helps distinguish between different models of dark matter. For instance, if dark matter is warm, moving relatively fast and smoothing out small-scale structure, then fewer small clumps will exist, and rings will be smoother. If dark matter is cold and clumpy, rings will be peppered with small anomalies. So each ring is a test of fundamental particle properties framed by an astronomical alignment. There's also a human aspect to this work. Finding rings often begins with a moment of wonder in the lab or at the telescope, someone scrolling through images and stopping cold. Cataloging and modeling them then becomes a slow communal craft, collaboration between observers who secure sharper images, spectroscopists who measure redshifts, and theorists who run the lens reconstructions. The process can span months or years, but each completed model yields a new piece of the puzzle, a measured mass, a mapped halo, or an upper limit on dark satellites. For graduate students and young researchers, an Einstein ring can be an entry point into a career-long fascination with cosmic structure and gravity. And finally, there's the philosophical bent. The candle-through-bottle analogy carries a humbling lesson. The universe often keeps its objects honest while reshaping their images. Things are as they are, but the routes we take to them change what we see. In those curves of light, we learn not only about the objects themselves, but about the medium they travel through, the geometry of space that, in Einstein's picture, is inseparable from the mass it contains. An Einstein ring is therefore not just a pretty loop. It's a conversation between light and gravity, a short sentence in the cosmos's long story about how matter and space interact. So when you next see an image of a delicate luminous ring around a distant galaxy, let yourself feel that double delight. First, the aesthetic thrill of symmetry and light. Second, the deeper thrill that every point on that circle carries information about mass, about unseen structure, about distances across the universe. That rim of light might be only the flame's reflection through a bottle, but it is also a measuring stick, a magnifier, and a map. In the curvature of its path, we read the quiet geometry that binds the cosmos together. Not everything bright is visible in ordinary light. Think about walking through a foggy street at night. The neon signs are still there, but their shapes soften, their colors shift, and entire storefronts can disappear into a gray wash. The heavens do the same thing, but with dust instead of fog, and that dust has a taste for blue light. A galaxy that looks like a faint, anonymous smudge in an optical photograph can suddenly burst into life when we put on infrared goggles. Switch again to radio, and you might see long, elegant jets drawn by invisible black holes that optical light never hinted at. That shift from invisible to vivid is what this subsection is about. It's not just science jargon. It's a change of perspective that shows how the universe is layered and how much of reality depends on the way we're looking. Dust in space is tiny, grains smaller than a smoke particle, but there is a lot of it. Those grains scatter and absorb short wavelength light, blues and ultraviolet, much more efficiently than long wavelengths, red, infrared, radio. The result is called extinction. Light is dimmed and reddened. A bright, young star cluster full of hot blue stars can sit behind a curtain of dust and look like, at best, a pale ember in optical light. Entire star-forming regions and even whole galaxies can be camouflaged. We see this in our own Milky Way. Look along the plane of the galaxy in optical light, and you'll notice dark lanes, not empty space, but dense interstellar dust blocking the starlight behind them. Those dark lanes are actually cradles for new stars. In optical, they are mysteries. In infrared, they become baby rooms full of crying newborns. How different wavelengths reveal different things. Each wavelength of light interacts with matter differently, so each tells us a different story. Infrared. Heat is the language of the infrared. Dust that looks opaque in visible light glows in the infrared because it's warmed by nearby stars. Infrared light passes through dust more easily, so telescopes like Spitzer and JWST and ground-based infrared observatories can peer into dusty nurseries and see protostars wrapped in envelopes of gas and dust. We suddenly find outstars forming, disks around young stars, and the warm skeletons of galaxies that look dull in optical images. Submillimeter and millimeter, ALMA territory. At these wavelengths, cold dust and molecular gas speak. ALMA gives us maps of dense clouds of gas, the raw material for stars, showing filamentary structures and collisions that will eventually collapse into new suns. Where optical sees nothing, ALMA shows where the action will happen. Radio. Radio waves reveal the most surprising, sometimes violent, parts of the universe. Supermassive black holes at the centers of galaxies can launch jets of relativistic particles that glow in radio wavelengths via synchrotron emission. These jets can stretch for hundreds of thousands of light years, sculpting the surrounding gas and even influencing star formation. Neutral hydrogen gas emits at 21 centimeters, and by mapping that emission we can trace a galaxy's rotation and mass distribution in a way optical light cannot. X-rays and gamma rays. Not our main focus here, but worth noting. The highest energy light detects shock fronts, superheated gas, and active nuclei that are invisible elsewhere. The layered tapestry metaphor. Imagine the sky as a richly woven tapestry. If you look only at one thread, you might admire its color but miss the pattern. Look at red threads and you see repetitive stripes. Switch to blue and you find a floral motif you never knew existed. Now step back and pull another thread, radio, infrared, ultraviolet, and the whole design changes. The galaxy you thought was simple becomes a complex work of art with hidden embroideries, star-forming rings, dust lanes, jets, shells from exploded stars. That layered seeing is not just poetic, it's essential. It forces humility. If astronomers had only optical telescopes a century ago, entire classes of objects, ultra-luminous infrared galaxies, cold molecular clouds, radio jets, would have remained unknown. Each wavelength removes a veil and adds a new truth. A galaxy behind dust is still a galaxy. It was only refusing to be seen in one register. Personal moment. Finding hidden structures. I'll never forget the first time I looked at a composite image that combined optical, infrared, and radio data. In the optical panel, the galaxy was pretty but unremarkable. In the infrared, a bright knot lit up, a star cluster forming behind a dust cloud. But the radio map? That's where I felt a small kind of awe. There were long, delicate plumes, like brushstrokes, radiating from the center, thrown there by a black hole's outflows. Things that seemed quiet were actually eloquent, speaking in a register I hadn't thought to listen to. That feeling of realizing something was astoundingly richer than I'd first perceived is familiar. It mirrors how we sometimes misjudge people or situations because we only see them in one light. We assume silence equals absence of feeling, calm equals nothing going on. But sometimes the most important things are happening behind the curtain. Scientific examples that make this real. The Orion Nebula. In visible light, it is spectacular, but infrared and radio reveal the dense protoplanetary disks, proplyds, around young stars and the flows of gas being sculpted by stellar winds. Without those wavelengths, we'd miss the earliest stages of planet formation, the antennae galaxies. In optical, they show dramatic tidal tales, but infrared images reveal sights of intense, dust-obscured starbursts, whole neighborhoods of massive stars being built behind veils. Centaurus. A. Optical images of this elliptical galaxy are interesting, but radio maps unveil huge jets and lobes powered by the central black hole, structures that extend far beyond the optical body of the galaxy. Supernova remnants. In optical, you might see a faint filament. In radio and X-rays, you can trace the shock front expanding, see magnetic fields being tangled, and find pulsars hidden in the glow. There's a moral here that I keep returning to. Layered seeing is kind. It teaches patience. When something, someone, a mood, a project, seems invisible or dull, it might just be waiting for the right kind of attention. That thought helps in small, human ways. If a friend is withdrawn, it doesn't necessarily mean they don't care. If a piece of work seems stalled, perhaps the next method, the different wavelength of approach, will bring its shape into relief. This is practical, not sentimental. Astronomers literally change instruments and wavelengths to find answers. In everyday life, we can change the way we look, shift the time of day, change the tone of our questions, switch from quick judgments to curiosity. It isn't a magic wand, but it helps us avoid the cruelty of assuming the worst because our first glance didn't reveal everything. A short reflective exercise for viewers. If you want to make this concrete, try a small experiment tonight. Think of a worry or a person who feels distant. For 1 minute, list the things you know about them only from the optical view. What's visible, immediate, loud. Then take another minute to imagine the infrared view. What warm, hidden things might be going on? What past events, soft feelings, or small efforts could be lighting that hidden warmth? Finally, for a third minute, ask what the radio view might reveal. The large-scale forces at play, faults or structures that are invisible at first glance. You may find what you imagined, or you may just notice that you feel a little less certain and a little more compassionate. Both are useful. When we look at the universe with just one kind of light, we see a surface. When we add infrared, radio, submillimeter, X-ray, we start to read the history and the physics stitched into that surface. The next part of our journey will take that idea further. We'll look at how these different threads of light not only reveal hidden structures, but also tell a story of cause and effect. How jets from black holes influence star formation, how supernovae enrich the next generation of stars, and how galaxies evolve when their different components interact. For now, hold the image of a dusty veil and a radio jet together in your mind. Let it be a small reminder. What you can't see right now may be waiting for a new kind of light. Patience and a willingness to change your viewpoint will often let the familiar take on a new and truer shape. Picture a galaxy as a living thing, not alive in the way you or I are, but with processes that inhale, exhale, and slow down when needed. Two of the most spectacular and important of those processes are the narrow, focused jets launched from around supermassive black holes and the broad, warm exhalations we call superwinds from starburst regions. One is a laser-like beam slicing into intergalactic space. The other is a soft, carrying breeze, full of the ash and seeds of future chemistry. Together, they are the breath of galaxies, slow, deep, necessary. Start with the very center of a galaxy, where a supermassive black hole sits. When gas, dust, or even a whole star spirals in, it forms a disk that whips around that hole at enormous speeds. Magnetic fields threading that disk and the spinning black hole get twisted and stretched by rotation. Under the right conditions, those tangled fields act like a nozzle. They collimate the infalling matter, squeezing it into twin, needle-thin beams, and fling that plasma outward at speeds close to light. Imagine water being squeezed through a garden hose nozzle, but replace the water with charged particles racing so fast that relativistic effects matter, and replace your shed's hose with magnetic field lines anchored in an accretion disk. The result is a relativistic jet, narrow, incredibly energetic, and strangely elegant. We see these jets in galaxies like M87, whose single luminous jet was one of the first things Hubble focused on, or in Cygnus A and Centaurus A, which sport brilliant radio lobes at distances much larger than their host galaxy. Those lobes, glowing like lanterns far from home, are the places where the jet finally slows, slams into surrounding gas, and lights up in radio and X-rays as particles spiral in magnetic fields. That light tells us of electrons moving at relativistic speeds and magnetic fields stretched over hundreds of thousands of light years. Those beams carry energy more than mass. They are not simply pouring the galaxy out. They are channeling enormous power along a tight axis. When the jet hits gas, the circumgalactic medium, or the hot plasma filling a galaxy cluster, it punches cavities, drives shock fronts, and inflates bubbles in the surrounding medium. Observations with X-ray telescopes like Chandra show these cavities clearly. Ghostly voids where the ambient hot gas has been pushed aside and the jet's energy has been deposited. Those cavities are cosmic versions of exhaled balloons, places where a galaxy has removed energy so the rest of it can remain balanced. There's a second way jets matter beyond merely looking spectacular. They regulate. If a central black hole allowed all infalling gas to cool and form stars freely, a galaxy could burn through its fuel in a short cosmic heartbeat. Instead, jets inject energy into the galactic atmosphere, heat it, stir it, and keep it from collapsing. In massive clusters, jets prevent the central hot gas from cooling catastrophically, the so-called cooling flow problem, by supplying steady heating over tens or hundreds of millions of years. In other words, jets act like brakes and thermostats at once. They're not trying to annihilate the galaxy. More often, they're moderating it, preventing a reckless sprint that would leave nothing for later. Now, shift your attention from the black hole's throat to dense regions of furious star formation. When a galaxy experiences a starburst, thousands or millions of massive stars are born in a relatively short time. Those stars live fast and die young. Their intense radiation and powerful stellar winds, followed by waves of supernova explosions, overlap and combine to create a colossal, overpressured bubble of hot gas. If that bubble finds a low-density path out of the galactic disk, it bursts through and a broad wind pours outward, a superwind. Superwinds are different from jets in a few key ways. They are slower, typically hundreds to a few thousand kilometers per second, rather than a substantial fraction of light speed. And they carry more mass. They pick up and drag along cooler clouds, dust and metals forged in the hearts of stars. The classic visual example is M82, the cigar galaxy, where deep images show a glowing, chimney-like outflow of gas and dust streaming away from the starburst core. You can almost imagine a galaxy exhaling smoke from a campfire, except the smoke here seeds the intergalactic medium with the elements necessary for future star and planet formation. Those metals are crucial: oxygen, carbon, iron. The heavy elements that make up planets and life are not created in abundance in the primordial gas of the universe. They come from stars. Superwinds take a galaxy's production and spread it outward, enriching the surrounding space. Over billions of years, these exhalations help build up the chemical complexity of the cosmic web, making pristine filaments richer and enabling new generations of galaxies and stars to form with a richer mix of ingredients. Superwinds also regulate star formation, but in a gentler way than jets. By removing gas or heating it so that it cannot collapse into new stars, a superwind throttles a galaxy's appetite. Think of it as pruning a garden. You don't destroy the soil, but you clear away the surplus shoots so the main plants can recover and flourish later. The timescales here are long, millions to tens of millions of years for a single outflow episode, so the effect is more like a deep breath than a violent sneeze. For the galaxy, that breath is one way to avoid burning all its fuel at once. Putting these two phenomena side by side, you can see a theme. Whether through needle-like jets or broad superwinds, galaxies have evolved mechanisms to manage energy and matter. They don't simply accumulate gas and convert it into stars until there's nothing left. They self-regulate. If too much gas piles into the center, the black hole wakes up, launches jets, and injects energy back into the system. If too many massive stars form in a cramped region, their collective winds and supernovae blow material away. Through both channels, galaxies pace themselves, releasing what they don't need and sharing what they can no longer hold. This regulation shows up in the properties of galaxies we observe. Massive elliptical galaxies are often red and dead, dominated by old stars and with little new star formation. Part of the reason is that their central black holes have, over time, repeatedly injected energy into the halo, preventing fresh gas from cooling and forming stars. In smaller galaxies, repeated superwinds can carry a large fraction of metals into the circumgalactic medium or beyond, reducing the gas available for new stars. Simulations of galaxy formation that include these feedback processes match observations far better than those that don't. If you remove jets and winds from the models, you get unrealistically bright, overly blue galaxies. The universe runs too hot. One of the most humbling aspects of these galactic breaths is their time scale. A single episode of AGN, active galactic nucleus. Jet activity might last a few million years. Superwinds from a starburst might continue for tens of millions. On human scales, those are unfathomable stretches of time. On cosmic scales, they're pulses in an ongoing rhythm. Galaxies don't gasp and immediately die. They inhale slowly, hold, and exhale over epochs longer than civilizations. The breath of a galaxy does not hurry. That slowness has a human lesson in it. We're used to rapid feedback cycles, the ping of a notification, the flicker of a deadline. In the cosmos, balance is achieved over durations we can barely imagine. The slow exhalation of metals and energy reshapes environments across hundreds of thousands of light years. The steady maintenance of a halo by radio jets can keep a galaxy from collapsing into hyperactivity for 1 billion years. The universe paces itself in ways that allow complexity to grow, given long, patient intervals. Observationally, we've seen both kinds of breathing at work. Radio telescopes expose the glowing lobes where jets deposit their energy. Optical and ultraviolet spectroscopy can detect outflowing gas in starbursts. Blue shifted lines tell us material is moving away from the galaxy. X-rays reveal hot bubbles in cavities where jets have evacuated the hot intracluster gas. And absorption lines in the spectra of background quasars let us map metals stretching far outside galaxies, evidence of past winds that carried enriched gas into the circumgalactic medium. Each wavelength gives a piece of the story. With radio, we image the lanterns, the lobes. With X-rays, we see the cavities. And with optical spectroscopy, we measure the speed and composition of winds. Together, they paint a picture of galaxies as dynamic breathing systems. It's also important to note nuance. Not every galaxy has strong jets, and not every star-forming region drives a superwind. The presence and dominance of these processes depend on environment, mass, and history. In rich clusters, central galaxies often show powerful radio mode feedback. In gas-rich, rapidly star-forming galaxies, superwinds are more common. Sometimes both operate. A galaxy can have an active nucleus and vigorous star formation, especially during a merger or a heavy feeding event. The balance of mass, energy, and magnetic fields determines which kind of breath dominates at any time. Two striking, almost archetypal examples help cement the contrast. M87's jet is a filament of light extending thousands of light years from a supermassive black hole with billions of solar masses. High-resolution images reveal knotty features, shocks, and synchrotron glow, the signpost of relativistic particles and strong magnetic fields. That jet not only looks dramatic, it sculpts the surrounding hot gas in the Virgo cluster and is a prime example of AGN maintenance feedback. By contrast, M82 is a nearby galaxy undergoing a starburst. Images show bright plumes leaving its disk, visible in optical emission lines, infrared dust emission, and soft X-rays. Spectra show outflowing gas rich in metals. M82's wind is a multi-phase flow, hot, X-ray emitting plasma carrying cooler clouds and dust, and it demonstrates how a galaxy can disperse its own chemical products into the environment. When you step back, there's a certain poetry to it. Jets and superwinds are not random tempests, but a form of breathing on a scale and pace that dwarfs human experience. Galaxies inhale material, process it into stars and black holes, and then, as necessary, exhale energy and elements back into the surrounding space. This breathing keeps them from exhausting themselves in a brief blaze of glory. It lets them live long enough to weave complexity into the cosmos. So next time you take a breath and feel the rhythm of your chest, remember, galaxies breathe too. Their breaths are slower, louder across light years, and filled with the raw stuff of creation. They pace themselves, let go of what they don't need, and share what they can no longer hold, making room for quieter seasons and for new things to grow when the winds have settled. What you're seeing out there isn't chaos so much as choreography, and the steps are slow. When a small galaxy wanders too close to a bigger one, gravity tugs at it like a distant hand. Stars are peeled off along the small galaxy's orbit and strewn outward, not in an explosive burst, but in long, elegant ribbons. Astronomers call these tidal streams, and they're some of the clearest evidence that galaxies grow by gentle, repeated gatherings rather than by dramatic smash-ups. Picture a thin ribbon of silk laid across a dark table. From a distance, it looks like a single line. Step closer, and you see it's made of fibers, threads that once belonged to another cloth. That's what stellar streams are. Threads of stars tracing the path their parent galaxy took as it spiraled in. The Sagittarius stream is the textbook example circling our own Milky Way. It wraps around us like a pale scarf, the remnants of a dwarf galaxy slowly being absorbed. Gaia, that treasure trove of precise stellar positions, has revealed dozens more, faint trails like handwriting on a dark page, each one a record of a past meal. It helps to slow down the mental clock. These processes play out over hundreds of millions of years. Up close, nothing looks like a car crash. Individual stars don't collide because space is mostly empty. What changes is their motion. Through tides and resonances, they trade momentum. One star moves out a bit, another shifts inward. Over time, the original dwarf dissolves. Its stars phase mix into the halo, and the streams fade. The signature is subtle. Density variations, a clump here, a thin tail there. But once you know how to read them, they tell the story of our galaxy's appetite as clearly as tree rings tell a tree's history. Resonances do their own quiet sculpting. Imagine dropping a pebble in a pond and watching rings ripple outward. In a galaxy, a passing satellite or a shifting gravitational pattern can set up similar waves, not in water, but in orbits. When many stars share orbits that experience the same gravitational nudges at the same rhythm, their paths collectively line up into rings or ripples. The Monoceros ring, a faint circular overdensity seen near the Milky Way's disk, may be the result of such orbital choreography. And in other galaxies we see even more dramatic ripples and shells, where a companion's passage set up coherent oscillations that hang on for eons. This is why the word violent can be misleading. The interactions are energetic when viewed on cosmic scales, but on the scale of individual stars, it's a dance, not a collision. The players trade energy and angular momentum like partners switching places. A dwarf galaxy can be stretched into a stream. A disk can be stirred so stars bob up and down in a wave, and yet almost no two stars ever physically touch. Gravity is the music, and time is the metronome. There's a comforting human quality to the way these traces fade. At first, a freshly accreted stream stands out, a tight, coherent line of stars with similar velocities and chemical fingerprints. Astronomers can follow it, map its orbit, and even work backward to infer the dwarf's history. But as billions of years pass, the stream's stars smear out in phase space. Their velocities diverge, their positions spread, and the pattern washes into the halo's background. Chemically, those stars still carry the element ratios that mark their origin, the way your accent or taste in food can whisper where you came from. But visually they become indistinguishable from native halo stars. The galaxy keeps the memory, but the memory becomes integrated into the whole. That's a potent image to hold up to our own lives. Think of the small galaxies as pieces of your past, relationships, old jobs, the neighborhoods you grew up in. At first, right after a move or a breakup or a big life change, those pieces seem sharp and separate. They have their own rhythms, their own orbits in your daily life. Over time, they thread into who you are. You don't lose them. You become a composite. If anything, those past paths are like the streams that shape the halo around you, faint influences that help define your current shape. I remember a moment that feels much like this galactic metaphor. A few years ago, I moved cities for work. At first, everything felt like an interloper. New routes to take, new coffee shops, new ways to order a bus ticket. Those habits, the old routes, the faces I'd known for years, were vivid and hard to let go of. But slowly, the new routines wove into my life. The unfamiliar streets softened into background. The old patterns didn't vanish. They showed up in the way I arranged my mornings or the tiny comforts I brought with me. Looking back now, it's hard to say where one life ended and the next began. The earlier version of me is still there, diffused into my present self, not erased, but absorbed. That's exactly what those pale, stellar streams do. They don't disappear so much as become part of a larger pattern. If you like, try this little exercise while watching the sky or even just sitting quietly. Imagine you're mapping your own halo. Take 3 things from your past: a person, a place, a belief, and picture each as a ribbon moving through space. How did it change your trajectory? Which ribbons are still tight and visible, and which have already washed into the background? If you pay attention, you'll probably notice that the things you thought were lost have actually been redistributed into the space you occupy now, giving you momentum in directions you might not have guessed. Back in space, astronomers use similar detective work. They look at the motions of stars, their chemical fingerprints, even their ages, to reconstruct merger histories. A stream's metallicity, the abundance of elements heavier than helium, acts like a signature of its birthplace. Dwarf galaxies tend to be metal-poor compared to large spirals, so when a patch of metal-poor stars moves together, it screams foreign origin. Combining chemistry and motion is called chemical tagging, and it's one of the ways we can tell that the halo really is a tapestry of past accretions. There's another layer that's quietly beautiful: the way these interactions can create structure where none existed before. A satellite's gravitational tug can trigger star formation in a disk, fold material into a ring, or set up waves that look like ripples on a pond. In other words, the galaxy's growth includes not just addition, but transformation. Pieces of the past are not simply stacked, they are bent and reworked into something new. That's an encouraging thought. Our past doesn't just get absorbed, it contributes to new forms, to fresh structure that carries its trace while being more than the sum of its parts. None of this erases the ache that can come with change. Grief, nostalgia, regret, those are real forces. But thinking of them as tidal streams reframes loss as integration. The past isn't a hole you left behind. It's a pattern threaded into your present. Over time, sharp edges soften. Old identities aren't discarded like trash. They're repurposed into the larger shape you now inhabit. And sometimes, if you step back, that larger shape looks gentle, inevitable, and oddly beautiful, like a galaxy's halo seen from far enough away that all the ribbons become a coherent glow. When we talk about cosmic mergers as quiet, we're not romanticizing the difficulties involved. Dwarf galaxies don't have feelings, but people do. A relationship ending, a career pivot, a place you can't return to. These are seismic to us. Still, the galaxy's slow-motion lessons can be useful. They invite patience. They suggest that time can turn sharp change into integrated strength. They remind us that the things we carry leave marks, even if those marks are subtle. So the next time you hear about a stellar stream or a ring around a galaxy, try to see more than an astronomical curiosity. See an archive, a palimpsest, the faded handwriting of past events. Notice how the universe keeps memory, not as a museum piece, but as material for the next shape to take. And if you feel like going outside tonight, look up for a few minutes. It's easy to think that only the bright things matter, the blazing stars, the fireworks of supernovae. But there is a quieter history written in the dim halos too. Those faint trails remind us that growth often happens through small, steady additions, and that our pasts, like those stars, are not lost, but woven into what we are now. Pause. Gentle music cue. Slow rise. We'll follow these threads a little further. Next, we'll look at how astronomers map those faint signatures and how that mapping acts like a family tree for galaxies. But before we do, take one more breath. Picture your own ribbons. Imagine how they have arranged you into the orbit you're in today. Not everything that comes from space arrives as light. Alongside the photons that paint our skies, there's another kind of traffic, tiny, fast, and often invisible. Cosmic rays and neutrinos. They're not flashy. They don't hang around for long. Most of the time they slip by unnoticed. But every so often one of them taps our detectors, and for a fraction of a second we're reading a message sent from far beyond. Picture, for a moment, standing under a thin rain. The drops are sparse and soft, not enough to soak you, just enough that you notice the sound of water on the roof. That's what particles from space are like. The roof, Earth's magnetic field and atmosphere, catches most of them. Some splatter and vanish in the upper air. A handful reach the ground. And a tiny, telling trickle gets recorded by instruments sitting quietly in mountains, deserts, and at the poles. Cosmic rays are the first kind of messenger we meet. They're not rays in the everyday sense. They're particles, mostly protons, a scatter of heavier atomic nuclei, occasionally an electron, They come in all energies. At low energies, there's a constant drizzle, products of solar activity and local sources. But once in a while, the universe sends a beast, an ultra-high energy cosmic ray, a particle with the energy of a well-served tennis ball packed into a single atomic nucleus, moving so fast it's hard to imagine. Where do those come from? That's part of the mystery. Most cosmic rays never travel in a straight line from their source to us. Because they carry electric charge, the magnetic fields threaded through our galaxy and around our planet bend their paths, scramble their directions. It's like trying to locate the origin of a tossed stone by looking at the splash pattern after it bounces off 100 invisible fences. Only the very highest energy cosmic rays retain some sense of direction. Lower energy ones arrive as an almost uniform, comforting noise. When these charged particles hit the top of our atmosphere, they do something dramatic. They collide with air molecules and produce cascades of secondary particles. Imagine a single energetic proton hitting an air nucleus and spawning dozens of new particles, which in turn hit more nuclei, creating thousands, even millions of offshoots in an expanding shower. Some of those secondaries are muons and electrons that punch all the way to the ground. Instruments on the surface, arrays of detectors spread across tens or hundreds of square kilometers. Count the brief arrival times and energies of these shower particles. Each detection is a timestamp, a tiny flash in a timeline that stretches back to the original event. These detectors are patient listeners. At observatories like the Pierre Auger Observatory, panels of scintillators and water tanks sense the charged particles and record coincidences. Arrays measure the pattern on the ground and reconstruct the direction and energy of the original cosmic ray. Somewhere, a processor writes "event detected," and the data is added to a catalog, a quiet archive of impacts. Those counts happen all the time. Sometimes they're routine. Sometimes they're extraordinary, a rare spike that sets people whispering about possible sources, a nearby supernova, an active galactic nucleus, a gamma-ray burst. Neutrinos are different in temperament. If cosmic rays are the rain that taps the roof, neutrinos are the air itself. They pass through the house and you, almost without noticing. Born in the same violent places, the core of our sun, the furnace of a supernova, the collision zones near black holes, and perhaps originating in the earliest moments after the Big Bang, neutrinos are incredibly light and interact so weakly with matter that billions pass through your body every second, and you're entirely unaware. That almost non-interaction is precisely why they're so valuable. A neutrino can leave the heart of a star and carry a story unscathed. Photons from a supernova can be delayed or scattered by dense material. Neutrinos escape immediately. In 1987, when a massive star exploded in the Large Magellanic Cloud, neutrino detectors around the world registered a handful of neutrinos hours before the first light reached telescopes. Those detections told astronomers, in a voice no other messenger could provide, that the core collapse had already happened inside the star. For a few minutes, instruments heard the inner workings of a dying star. Catching neutrinos requires scale and patience. The detection trick is to watch for the rare occasions when a neutrino does interact. Large tanks of ultra-pure water or ice, instrumented with arrays of sensitive light detectors, watch for the faint cone of Cherenkov light produced when a charged particle, spawned by a neutrino interaction, races faster than light does through that medium. Super Kamio Kandy in Japan, SNO in Canada, and ice cube at the South Pole are built on the principle of volume. Make enough target material and wait long enough, and even these ghostly visitors will leave an imprint. Even then, detections are sparse. For the majority of neutrinos that come from the sun, a cubic meter of your backyard would see none of them. A detector the size of a small swimming pool might record a few per hour from the sun, and just a handful of higher energy neutrinos from distant astrophysical sources per year. Yet those handfuls matter hugely. The ice cube detector, buried deep in Antarctic ice, listens for tiny bursts of blue light and occasionally flags a high-energy neutrino whose direction points back toward a blazar, a super-bright galactic nucleus aimed at us, and inspires coordinated observations across telescopes. That was the moment multi-messenger astronomy really began to feel like a living conversation between different cosmic witnesses. There's another quiet marvel here. These messengers carry complementary information. Photons tell us about surfaces and outer layers. Charged particles trace magnetic paths and shock fronts. Neutrinos tell us about dense interiors in the earliest instance of violent events. By combining their traces, we can reconstruct a fuller narrative of what happened many light years away. It's like hearing different instruments in an orchestra. Each one plays a part, and together they make a piece we could never appreciate from a single note. On a personal level, thinking about these particles can be both humbling and oddly comforting. I like to imagine lying awake on a summer night, looking up at a velvet sky, and knowing that the silence is deceptive. While I'm half asleep, a parade of tiny couriers is passing through me and my house. Most of them I will never notice. Some will get caught by stone and steel, registering as a single blip on a distant machine. A few, perhaps, will tell us something surprising about a faraway event. There's a solace in that, a sense that the universe is persistently, patiently sending information, unbothered by whether we listen right now. You don't have to be a scientist to enjoy that fact. If you've ever received a handwritten letter in the mail, something rare now, you know the pleasure of a private message. A cosmic ray is like a postcard pinned through the atmosphere, smudged and bent, but bearing a stamp from a violent place. A neutrino is a note that slid through the keyhole, arriving unmarred. The thrill comes when the note contains a word we didn't expect. It's also important to hold two truths at once. These particles are tiny and quiet, and their presence is profoundly informative. Most of the time, they don't do anything dramatic to us. They don't change our daily lives. But when they interact with instruments, we gain windows into processes that no telescope could otherwise open. The detections are sparse because the universe is mostly empty, and because the physics that governs these interactions is subtle. But even sparse data, when pieced together, rewrites our understanding. And that brings us back to the rain on the roof. If the night were alive to your ears, you wouldn't hear explosions. You'd hear soft, steady pings. Each ping would have its own rhythm and origin. You couldn't be expected to catch every single drop. You'd simply take comfort in the sound, in the fact that something is happening out there, that the world keeps transmitting small notes across the void. Maybe you'd stand for a minute on the porch, listen, and feel connected to all the distant places that produced those sounds. Let that be enough for now. You don't need to map every particle's path or catalog every neutrino that brushes past you. It's soothing to know that the roof exists, that Earth stands between you and a cosmos of messengers, and that the rain is gentle. At any time, if curiosity calls, There are people and instruments ready to catch a drop, to translate a tiny flash into a story. Until then, there's comfort in the patient, ongoing conversation of the universe, small signals sent across impossible distances, waiting for us to listen when we're ready. Think of the sky as a window, not the kind you can open, but the kind with a frame, the 2x3 rectangle that channels everything you see into one tidy view. That frame is the observable universe. There's a farthest distance from which light has had time to reach us since the universe first became transparent. After the fog of the early cosmos thinned and photons could finally travel freely. Once you account for the fact that space itself has been stretching the whole time, that distance works out to a sphere about 46 billion light-years in radius. That's the edge of what we can see. That's the edge of our window. But this is where the language matters. Edge sounds final, like a cliff you bump into and nothing exists beyond it. That's the wrong picture. Beyond our sphere, more space continues, possibly forever. The universe doesn't stop at 46 billion light-years. It just stops being illuminated to us. Why does this happen? Two main ideas. First, the universe is only so old, roughly 13.8 billion years. Light has a limited time to travel. Second, space itself is expanding, and that's key. A photon that left a distant galaxy billions of years ago has been traveling toward us while the space between has stretched. That stretching makes the source of that light now much farther away than the distance the photon covered to reach us. That's why the observable radius is far bigger than 13.8 billion light-years. It's like someone waving from a moving boat while the ocean itself is stretching under you. They may have been close enough when they waved, but the water carrying them has drifted. The wave still reaches you if it had time, but the boat is much farther away now. So inside that sphere is everything whose light, ever since the universe turned transparent, has reached our eyes or our telescopes. That's the complete story for what we can, in principle, observe. But there's another twist. Expansion is accelerating. Because of dark energy, the expansion rate is increasing. That means regions of space are pulling away from us faster and faster. Some patches of the universe are receding at speeds such that no light they emit now will ever make it to us. They exist. They're real. They'll remain forever outside our view. That's not hypothetical. General relativity predicts horizons like this when expansion outpaces light's ability to bridge the stretching space. There's a subtle but important distinction. The particle horizon versus the event horizon. The particle horizon is the limit of what we've seen so far, shaped by the universe's age and its expansion history. The event horizon is a different boundary. It separates events that we could, in principle, ever see from those we can't, even if we waited forever. Because expansion is accelerating, some regions are permanently beyond that event horizon. They are part of the full universe, but inaccessible to us now and always. When I first learned this, I felt a tiny lurch, a kind of cosmic claustrophobia. The idea that there are real galaxies we can never, ever see felt like being locked in a beautiful room with the curtains drawn. I imagined great lighted cities out there, just beyond reach. For a moment it was unsettling, but then I started looking at it differently. Think about any framed view, a painting, a photograph, a window looking over a courtyard. Boundaries don't always limit us. Sometimes they make what's visible more meaningful. A frame focuses attention. It lets the eye rest. It gives the mind a place to land. Imagine a book that ends with a perfect last sentence. You close it and feel complete. Maybe there are other chapters somewhere else in the library, maybe not. But that final line gave you closure. Inside this circle of visibility, the story is complete for now. We can read every page that exists in our light cone. We can map it, measure it, tell stories about it. If more pages exist elsewhere, beyond our event horizon, they will not disturb our sleep. Let the window be enough. Let it hold the stars steady while you breathe. For a helpful mental map, there's also the Hubble sphere, the distance at which galaxies are presently receding at the speed of light. It's smaller than the full observable sphere. Some galaxies we see today are outside that Hubble sphere because their light started traveling toward us long ago when they were closer. The light rode the expanding fabric of space to reach us. But if a galaxy lies beyond our event horizon, its light will never reach us no matter how long we wait. That might sound like a limitation, but I find it comforting. A visible boundary gives us certainty. In a universe that is otherwise unimaginably vast, the observable patch is ours to explore fully. It's the laboratory we can measure. It's the garden we can walk through and catalog. We can learn its laws, its history, its texture. That is not small. Everything we know about atoms, stars, galaxies, the cosmic web, the very recipe that cooked up the elements in the first few minutes, all that knowledge comes from inside this framed sphere. Inside it, the universe feels intimate. It's a place where experiments work and predictions can be tested. The fact that beyond the frame there may be more, even different, doesn't diminish the value of what's inside. There's also something human in the discomfort with not knowing. We want to peek behind the curtain. We want to be cosmic voyeurs. That's a beautiful part of curiosity. It drove us to build telescopes, rockets, and entire fields of physics. But there's a lesson here that's almost meditative. You can love the mystery and still make peace with your limits. So what can you take away from this? First, the edge of the observable universe is real, but not catastrophic. It's a limit of information, not of being. Second, some regions are part of reality but forever out of view because of accelerating expansion, an honest, cosmic unknown. Third, and most importantly for how you feel sitting under the sky tonight, your view, framed though it is rich. It contains everything you can ever study, touch, and understand from here. That's a grand, reassuring thing. Next time you stand beneath the stars, imagine the circle of visibility as your window, deliberately drawn, beautifully filled. Count the galaxies you can count. Listen to the story they tell, and let the rest be silent company beyond the glass. You don't need the whole universe to feel the awe it inspires. The frame helps you hold it. Let the window be enough. Let it hold the stars steady while you breathe. If you let your imagination keep walking forward, past the bright fireworks of galaxy collisions and supernovae, you'll come to a very different kind of finale. Not an explosion, but a long, graceful dimming. The story doesn't stop, because everything vanishes all at once. Instead, the cosmos slows its pace, like a crowd that has applauded and is now filing out of a theater under a soft, warm glow. Start with the fuel. Stars are born from cold clouds of gas and dust. Over time, that gas gets used up. It forms stars. It gets locked into planets. It gets blown away by winds and radiation. The rate at which new stars form will taper off. The universe that is bustling now, full of birthplaces and blue-white beacons, gradually becomes less fertile. Galaxies will still exist, but they'll be quieter, their star-forming reservoirs less and less generous. That change happens in order. The most massive, hottest stars, the brilliant blues and whites that dominate pictures of stellar nurseries, burn so hot they burn fast. Those titans exhaust their fuel in millions of years, end in spectacular supernovae, and enrich their surroundings with heavy elements. Next in line are stars like our sun. They last billions of years. They leave white dwarfs behind and along the way seed planets and life. But the longest-lived characters in this cosmic drama are the small, dim red dwarfs. They barely sip their fuel and can shine for trillions upon trillions of years, so slowly that they never swell into dramatic finales. They fade like candle flames gently reduced to embers. Eventually, even those embers go out. The sun will become a white dwarf, a dense, hot ember roughly the size of Earth, but packing the mass of the sun. Those white dwarfs do not explode. They simply glow, gradually radiating away their heat. Over unimaginably long stretches of time, they cool and dim. We call the hypothetical, fully cooled objects black dwarfs. But it's worth noting, the universe isn't old enough yet to host any of them. They're a forecast, not a sight. And then there are the black holes, the ultimate sinks of mass and energy. Once thought to be eternal prisons, we now understand, thanks to quantum mechanics and Stephen Hawking's insight, that black holes are not completely black. They leak energy slowly, a process so glacial that a stellar mass black hole needs something like 10 to 67 years to evaporate. Supermassive black holes, the monsters at galactic centers, take far longer. Estimates spread, and the numbers get staggeringly large. But the point is the same. Even those titans will, in principle, fade. The final stages of their evaporation would briefly be energetic and strange, but for the universe as a whole, those sparks are the dying twinkles in an incredibly long dimming. There is a further, deeper possibility that matter itself might not be permanent. Some theories predict protons, the building blocks of atoms, could decay on timescales well beyond anything human societies or even biological evolution have ever seen. If that happens, atoms will slowly unravel into lighter particles, and the last complex structures will dissolve into near nothingness. Whether or not this is the case, the long-term trend is toward fewer places where energy can be usefully concentrated. All of this is often summarized under the label heat death, but that phrase can be misleading. It evokes frantic thermal destruction when what actually is meant is the draining away of free energy gradients. Heat death isn't a violent crash. It's the settling of the universe into a state where there's no organized way to do work. Energy still exists, but it's diffuse, evenly spread, and unable to drive the sorts of processes that build stars, life, or machines. That might sound bleak, but there's a different way to feel it. Imagine the lights in a theater dimming after a play. The actors bow, the audience rises, and people leave, not in panic, but in gentle conversation. The stage lights relax. Dust hangs in the soft beam and looks almost beautiful. The curtains close, and what remains is a kind of satisfied silence. There is no failure in that quiet. Work was done. The energy was spent in performance, creation, and shared experience. The dimming is the natural conclusion to that giving away of energy. It also helps to keep the timescales in mind. None of this is soon. Our sun still has billions of years left of stable life. The brilliant blue stars are dying and being replaced every few million years. Yes, but the slow fade of the cosmos takes place on timescales so vast they are almost beyond human comprehension. Trillions, quadrillions, numbers with more zeros than you might picture comfortably. If imagining the universe as a single lifespan is too abstract, think instead of the difference between an afternoon concert and a lifetime. The final exhale of the cosmos is more like the seasons dropping into a long winter after many, many harvests. That perspective can be oddly calming. The cosmic quiet is not urgent. It's gradual, permitted, inevitable. It invites a different emotional response than panic or melancholia. There is dignity in winding down. There is space for a kind of rest that comes from completion rather than loss. Which brings us gently back to here and now. The sky above us is lively, radiant, and full of beginnings. When you look up, you are seeing the universe in a phase awash with potential. Stars forming, worlds coalescing, chemistry arranging itself into novel complexity. You are, by cosmic standards, in an era of generous energy and creative possibility. And so, your task tonight is intentionally small and human. Let your own energy drift toward rest and carry only what is light. What does that mean in practical terms? It doesn't require cosmic renunciation. It means a few things that anyone can try, right here and now. Notice what feels heavy and what feels light. Take a moment to name one thing you can put down: a worry, a task, a stubborn irritation. Don't try to fix it. Just recognize it and set it aside mentally for the night. Like stored gas that will eventually feed a star. Some worries are useful. Many are not. Slow your breath. The universe's ending is measured in stretches so long they dwarf human concerns, but you can practice a smaller scale slowing. Take 3 slow breaths. Inhale for 4 counts, hold for 2, exhale for 6. With each exhale, imagine carrying less weight. With each inhale, bring in a cooler, lighter sense of perspective. Let your attention rest on small, light things. Look for physical light, a lamp, a candle, a screen's glow. Or look inward for a light memory, a kind word you received, a comfortable seat, the taste of something you enjoyed today. These are the light things the line asked you to carry. Small, nourishing, not burdensome. There is also an invitation here to accept endings in our lives without forcing drama where it need not be. Relationships change, jobs end, seasons shift. Not every ending needs to scream for attention. Some deserve the faint footfalls of people leaving the theater, the soft rustle of coats, the quiet closure of doors. When endings are handled with care, they make space for whatever comes next. You might feel strange letting go, especially if the modern tendency is to fight, to optimize, to fix. The cosmos itself is showing us a softer option. After the energy has been shared, after the stars have done their work of forging atoms and scattering them, what follows is not punishment, but rest. Imagine the pride of repairmen who know there will be no more repairs because everything was attended to thoroughly. Imagine a musician's relief after the last note has been played well. For those who find comfort in the technical detail, consider that even the most dramatic astronomical events only briefly punctuate the universe's long, quiet stretches. Supernovae and gamma-ray bursts are spectacular but rare in the grand sweep. Between them lies a thickness of ordinary brilliance, slow-burning red dwarfs, patient white dwarfs cooling, planets turning in steady orbits. The vast majority of cosmic time will be spent in that ordinary brightness, and then in a very gradual dimming. That ordinariness is a kind of beauty, and if you worry that accepting quiet is the same as giving up, think of it instead as choosing where to place your energy. You cannot reheat the universe. You cannot forestall the long-term fate of matter and black holes, but you can decide what to animate, what to tend, and what to release. Let the big, immutable timelines be a kind of permission slip to stop lugging around what's unnecessary. There is also room for wonder in this slow fade. Imagine a future civilization, if one could exist, watching the rest of the galaxy dim and learning to create meaning in smaller pools of energy, finding ways to tell stories in longer breaths. There is creativity in constraints. The theater darkens, but people can still talk, remember, and hold warm hands. It's a different intimacy, but not a lesser one. So tonight, as you prepare to leave the day behind, think of the theater metaphor and let it tailor your actions. Clear a small mental space. Turn off the bright, gratuitous lights of worry. Keep what is light, a kind word you can give yourself, a simple ritual that centers you, a plan for tomorrow that is modest and kind. Rest, not as defeat, but as a conscious, graceful choice. The universe's final silence, if there is to be one, is not an indictment of meaning. It is the quiet that follows work well done. And just as stars once shone brilliantly and fulfilled their roles, you too can let your energy be spent in ways that feel meaningful. And then, having done the work, allow yourself to drift to rest. When you're ready, breathe in once more. Hold that lightness for a moment, and exhale. Carry only what is light. Think about the materials that make you. The carbon in your cells, the calcium in your bones, the iron that carries oxygen in your blood. None of that was made in the peaceful dim of our little sun. Those atoms spent their first lives inside other stars. They were born in fire, fused from simpler stuff, and then thrown back into space when those stars ended their lives in explosions or long, slow winds. So when you trace your finger along the rim of a coffee cup, when you stand barefoot on the earth, or when you close your eyes and remember a particular song, you're touching a history that began long before the sun existed. Your body is, in a literal sense, a small archive of stellar histories, tiny remnants of ancient fires rearranged into a pattern that can notice sunsets, appreciate a melody, or enjoy the quiet of a room. That's an odd, beautiful thing to hold in your head. The universe, which once had no eyes or ears at all, has arranged some of its atoms into a system that can look back and feel. Not grandly, not as if the cosmos appointed a single representative, but simply, softly, in the fact that matter became aware. You are one of the ways the universe knows itself, and it works both ways in a small, tender loop. When you read about a distant galaxy, when you learn the trajectory of a comet or the story of a star's death, you are doing something the universe participated in. Those galaxies, in a sense, are listening back through you, through a mind assembled from the very particles they produced. The galaxies aren't conscious listeners, of course, but the fact remains. What was scattered by ancient light is, for a while, gathered into a mind that can understand and feel. Let that idea sink in for a moment. Let it make you lighter, not heavier. You do not have to carry the weight of everything that ever happened in the universe. You are not responsible for the stars. You are allowed to breathe. What began as fire becomes calm. Those hot, violent processes that built the elements ended up scattering their gifts across space, and the raw material of ancient thermonuclear furnaces found its way into clouds of gas and dust. Over time, gravity brought some of that dust together. Planets formed. One of those planets, our Earth, became a stage where atoms could assemble into cells, and cells into bodies capable of awareness. Think of your body as a small, living museum. In it are artifacts of stellar life cycles, elements that once swirled inside suns colder or hotter than our own, elements that tell stories of pressure and heat we can barely imagine. But what's extraordinary is not just the chemical history, it's the emergent property that arises when those elements are arranged in particular ways. That arrangement, your nervous system, your memories, your capacity to notice, means the universe, quite literally, can look back at itself. You don't need to feel special to experience this. The phrase "the universe knows itself" isn't an ego boost or a cosmic certificate. It's a humble fact with a generous heart. It says, some part of the universe has become capable of wonder, and that part includes you. And there are practical, quiet implications to that. You can let curiosity be an act of connection. When you marvel at a comet, you are continuing a process that began in stellar furnaces. When you sit with a friend and share a sunset, you are turning scattered atoms into a shared present. The universe doesn't demand anything grand of you. It simply offers the chance to be present. So give yourself permission to rest in the truth of this. You are made of the same stuff as the stars, and through your senses and your thoughts, that stuff becomes a kind of noticing. You are not the keeper of the cosmos. You are its rest, like a leaf on deep water. Imagine a quiet lake, deep and still. Put a leaf on it. The leaf doesn't hold the lake. It simply floats, cradled. It rides the surface, carried by currents larger than itself. In the same way, you can let the vastness around you bear you. You don't have to fix the universe or fully understand it in one sitting. You only need to be held in it for a while. There is also comfort in the impermanence of it. The elements that made you didn't stop being part of the universe when they joined your body. They will keep circulating, joining new stories, entering new lives in ways we can't predict. What was scattered became whole for a while in you. That, for a while, doesn't diminish its meaning. If anything, it blesses it, because it means every living moment is a rare, temporary convergence of histories converging in a single consciousness. And maybe that helps with the hard parts. On days when you feel small or irrelevant, remind yourself that smallness doesn't equal insignificance. A single mind, a single pair of eyes, a single pair of hands can notice and respond. You can hold tenderness, curiosity, and care. You can listen to music or watch a sunset, and in doing so, participate in an unfolding story that began in stars. You could think of this as permission to lighten your shoulders. You don't need to compress the universe into answers or explanations right now. Knowing you are stardust doesn't force you to solve anything. It offers perspective, and sometimes perspective is enough. If it's helpful, try this. Next time you feel overwhelmed, place your hand over your heart. Feel the rhythm. Remember that the iron in your blood once lived inside a star. Let that thought be a kind of lullaby, not a grand sermon, but a small, warm fact you can tuck into your pocket. And when you read about galaxies or watch a documentary about the life cycles of stars, don't feel like you are absorbing knowledge in isolation. You're part of a conversation that stretches back billions of years and will continue after you're gone. The stars made the parts of you that can understand stars. That's a quiet continuity that connects micro and macro in an intimate way. So here's the practical takeaway. Treat the fact that you're made of stars like a soft invitation. Let it make you more curious, not more burdened. Let it make you kinder, not more pressured. Let it remind you that presence, really showing up for a piece of music, a conversation, or a sunset, is itself a cosmic act. You are a brief arrangement of ancient light. You are the universe noticing itself. Let that be a comfort as much as a wonder. Let it be a reason to rest, to be curious, and to be gently present for yourself and for those around you. We have wandered through old light, quiet gravity, and patient structures, and the night is still the same, wide, steady, welcoming. If you are still awake, let the next breath be slower than the one before, not forced, just a gentle lengthening, like a tide rolling in a hair's breadth farther than it did a moment ago. Feel it travel down into the chest. Feel the ribs ease outward. And on the soft exhale, imagine something loosening you didn't even know you were holding. Picture the Milky Way as a pale river arching over a sleeping landscape. The band of stars is thin and familiar, like lanterns hung across a long, dark stretch of sky. You might see that river from a place you know, a field behind your childhood home, a hill on a night you stayed up later than you were supposed to, or even the quiet rooftop where you once counted satellites. Let that memory sit for a second without needing to be important. It can be ordinary, small, and exact, precisely the kind of thing the universe would approve of. Now, imagine your thoughts as small boats easing toward the shore. Each one glides, unhurried, its lights dimming as it finds a place to rest. There is no need to chase them or pull them back. Just watch them settle. A worry that has been circling, hand it a name if it helps, or don't, and let it drift. A plan that feels urgent, place it gently in a boat and let the current take it. Notice how it is easier to let go when the world around you feels vast and patient. Vastness does not push, it simply gives space. The universe asks nothing from you right now. There are no immediate tasks stamped across the sky, no deadline holding the moon hostage. It does not need answers or speed. It offers distance so your worries can look small, and time so your body can find its own rhythm again. This is not pressure to be productive with your rest. It is permission to be human and to let the human parts soften. If your shoulders are carrying the day like a bag of groceries, let them set that bag down. Feel the weight release into the place that supports you, your chair, your bed, the mattress that remembers your shape. When your eyes grow heavy, let them drift closed like curtains finding their groove. Don't fight the darkness. Think of it as a velvet backdrop for the small lights you carry. When your shoulders soften, let them stay that way. Let your jaw unclench. Let the tongue rest. There is a kind of grace in small surrender. Somewhere, beyond any city lights or everyday noise, a supernova remnant keeps expanding. Imagine the ghost of that explosion, dust and gas thinning outward. A slow, unhurried bloom that will take millennia to forget. That expansion is not frantic. It is the patient aftermath of a fire that burned impossibly bright and then moved on. In the same breath, somewhere else, a newborn star takes its first light. A cloud, dense and quiet, begins to glow because particles found the courage to cluster. These two events, an ending and a beginning, coexist in the dark. There is room for both to happen at once, and that tells you something. Endings do not erase beginnings, and beginnings do not dismiss endings. Both can be part of the same wide sky. You are safe here. You are small in the best possible way. Small enough that a single breath can change your internal weather. Small enough that you can fold yourself into a corner of the universe and be hidden and held. That smallness is a relief. It means no one is waiting for you to hold everything. It means gravity is gentle on you and kind in a way you can feel. Being small is not loneliness. It is intimacy with the world. The fact that the same atoms that make up your hands once swirled in the bellies of stars, and now they are warm because you are alive and because some distant light is passing through dust to find you. Bring your attention back to the body, if it has wandered. Notice how the breath travels now, not in a rush, but in a slow, simple exchange. Inhale the quiet. Exhale the tension. With each out-breath, imagine sending small, careful letters to the edges of your awareness. I will be okay for a little while. This can wait. I am allowed to rest. Say them aloud if your space allows, or hold them like a private benediction in your mind. If your thought feels loud, names, tasks, the overlay of modern life, picture a field at dusk where the crickets do not try to outsing the wind. Each sound has its own space. Let the loud thoughts become part of that field, present but not commanding. Watch them lower their voices. They don't need to be silenced. They simply need to be met with a calmer rhythm. Think of this moment as a kind of homecoming. You don't have to earn the right to it. There is nothing to report, no performance to assess. The sky above you is a listener that does not judge. It has room for grief and for gratitude in the same wide breath. If a memory comes, soft or sharp, let it have its moment and then tuck it into a pocket of night where it can rest until you choose to visit again. Sometimes people worry that rest is a passive thing, that sleeping means letting life pass by, but rest is active in a different register. It is the body's way of repairing the gearbox, of returning the spark to its original steady hum. Imagine your neurons as a lantern that needs refueling. Sleep is the slow, kind act of refilling. It is not indulgent but essential. Allowing yourself to rest is an act of care for the world you will meet tomorrow and for the person who will be doing the meeting. If you keep finding resistance, plans that are uncomfortable to pause, emails that whisper, write them down on a small scrap of paper or in a note on your phone. Tell them, "I have recorded you. You are not lost." Then, close the page. The cosmos has already handled the big cycles. Your small circuits can take a tiny break. Imagine now a slow panorama moving overhead, constellations like familiar friends reclining on their routines, a comet tracing a gentle comment across the sky, and the Milky Way moving like river light across the dome. You are a brief, bright presence in a long, patient story. That is a good thing. It means you are capable of surprise and tenderness, and that you are allowed to conclude one day and begin another without dramatic ceremony. Before sleep takes you, rest with a small promise that you will meet tomorrow gentle on yourself, not because everything will be solved, but because you have chosen to return rested, which is the truest thing you can give to any challenge. Imagine waking with a breath already aligned to the universe's slow clock. You do not have to solve the infinite now. You only need to be present to the small, steady tasks that come. If your body wants to shift, turn a hand, rearrange a blanket, do so with ease, and then return to the quiet. These small movements are part of your language with comfort. There is no correct posture for rest, only comfort that allows the breath to deepen without effort. Listen for a moment to the soft sounds around you, the rustle of fabric, a distant car, the hush of air. Let them be a gentle percussion, a simple tempo for your rest. They are not interruptions. They are proof of life continuing, a reassuring metronome that says, whatever happens, the world will carry on, and you will not be the only thing that pauses. As your eyelids drop completely, imagine the boats, those small thoughts, mooring at the bank. They have found their place. The river of stars continues to arch and cool above the sleeping landscape. Somewhere a supernova remnant keeps expanding with patient confidence. Somewhere a newborn star is taking its very first light, tender and bright and tiny. You are part of that procession of ending and beginning. That is enough. If you need a final instruction, let it be this. Do nothing complicated. Breathe slowly. Allow whatever tension you're holding to melt with each out-breath. Let your body make the decisions now. If sleep comes, accept it without ceremony. If it stays away a while longer, stay with the quiet and keep your breaths long and unhurried. You are welcome to linger in this gentle watching for as long as you need. Here in the low hum of night and the wide openness of space, you are safe, small in the best possible way, and part of everything that glows. Let that thought carry you, soft and true, into whatever rest finds you.